Okay, welcome everybody to the first day of our second year of summer school on Trustworthy AI for Environmental Sciences. I am Amy McGovern. I'm the director for the TAI4ES, which is our NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. I want to start by welcoming all of you and acknowledging all of our co-sponsors. This event is being co-sponsored, TAI4ES is running it, NCAR is helping us and co-sponsoring it, as well as Google Cloud and LEAP, which is an NSF STC, and then Radiant Earth Foundation, who are helping with hosting the data sets that you're going to be using for the Trustathon. And this, of course, is NSF funded. If you can go to the next slide. So before we get into sort of what we're doing, I wanted to give you a quick overview of who we are, why TAI4ES is running this summer school. So we are the NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. Our short version is TAI4ES. Our goal is that we are developing novel, physically based, meaning it's based in the laws of physics, AI techniques that are demonstrated to be trustworthy, meaning we are actually checking with our end users about what it means to be trustworthy, why it's trusted and why it isn't. And we're going to go into a lot of that over this next 4 days of summer school. And that these will directly improve the prediction, understanding, and communication of high-impact environmental hazards. And we're going to hit a lot of these terms over the next few days of summer school. We're going to talk about prediction and understanding and communication in all of the different application areas. I want to point out all of our partners. So TAI4ES is led by the University of Oklahoma. We have Texas A&M Corpus Christi, North Carolina State University, Colorado State University, University of Albany, University of Washington, and Central Michigan University, as well as Del Mar College, who are developing, Del Mar is developing our AI community college curriculum. And then we are partners with NOAA, and our Google, IBM through the Weather Company, NVIDIA, Disaster Technology, Xerox PARC, Vaisala, and Radiant Earth, and a new partner, True Weather. If you want to learn more, you can follow us on our website and also follow us on Twitter, which I forgot to put the Twitter handle on the side, but it's at AI2Enviro. Next slide. Just giving a quick overview of everything that we do. Our research focuses on the synergistic cycle of trustworthy AI, where we're developing new physics-based AI, explainable AI techniques, robust AI techniques, and uncertainty quantification, all focused on a variety of environmental science applications, including convective hazards, winter weather, coastal environment, tropical cyclones, and subseasonal to seasonal prediction. And we're working together hand in hand with risk communication social scientists who will be doing a lot of the talking today to actually understand what it means to be trustworthy and figuring out why the AI is trustworthy and why it isn't trustworthy in the eyes of our end users and what we can do to improve our AI. As another part of what TAI4ES does, we work on broadening participation in workforce development, of which this summer school is a key part of workforce development. It is available online live today and available online for anybody in the future. We're working on training the workforce in all of you in improving our understanding of trustworthy AI. The circle that goes around all of this is new in our graphic, highlighting the focus that we have on ethical and responsible AI, as well as the fact that we are very focused on user-inspired AI. Next slide. The goals of the summer school are that we want to share our work in TAI4ES. We've been around for 2 years now on trustworthy AI with researchers and students worldwide. We want to engage researchers outside of TAI4ES, normal collaborators, to work on trustworthy AI. We want to build the global community of trustworthy AI researchers, and we want to serve as a nexus for trustworthy AI. And somehow, somewhere, my slides got edited. It was supposed to say nexus for, not nexus of. Anyway, next slide. The way that this will work is we have an intertwined set of lectures and hands-on activities. The morning, which is right now for us. I know that many of you from the Slack channel have been talking about that it's not morning for you. Right now, our time zones are Mountain Time. The morning is focusing on the foundational topics and trust and communication and risk communication, and the afternoon is focusing on the hands-on topics. Each day has a theme to what we'll be doing. So today we'll be talking about trust, interdisciplinary research, and then beginning explainable AI. Tomorrow we'll be talking about explainability and interpretability from the lens of the risk communication, and then also doing a specific XAI methods, primarily focused tomorrow on deep learning. Day 3, we're talking about trust and what that means with your data and how your data affects trust. And then day 4 is a focus on uncertainty quantification. And each day, the topics that are covered in the morning will help with the afternoon goals that we have set aside for the Trustathon. Next slide. And now we'll hand it over to DJ to talk about the Trustathon.
So good morning, everyone. My name is David John Gagne. I'm a machine learning scientist at the National Center for Atmospheric Research, and I'm the lead organizer for the Trustathon portion of the summer school. Next slide. So the unique idea of our Trustathon is that we wanted to take the kind of usual approach to a machine learning hackathon and sort of turn it on its head. So instead of focusing on trying to solve the problem with better training a better model or kind of doing a hyperparameter tuning exercise, we wanted to take the AI2ES approach and approach some different challenge problems from a user-centered perspective, and think about what, given a set of users that we would expect to be involved with a given kind of problem, think about it from their perspective and identify ways we can build trust in a machine learning method for the earth sciences and evaluate whether the machine learning method is actually trustworthy. So for this problem, we've got 3 data sets. One is severe weather, one is space weather, and one is tropical cyclones. So we kind of cover a decently wide space of the Earth, Earth system. Of course, leaves out quite a few other parts, but we hope that this kind of addresses sort of different aspects of the problem and different challenges in interesting ways. For each of these problems, we have a set of user personas, and these are sort of descriptions of an end user that you'll be taking your model and sort of developing with this end user in mind and thinking about how to communicate about the model with this end user. So next slide. So the way this is going to work is that the participants are randomly assigned to a team, a challenge problem, and a user persona with groupings by time zone. So if you're in the United States, you'll be grouped with other people that are kind of in a similar United States time zone. If you're in Europe, you'll be grouped with other people in similar European time zones, or Africa or Asia. The kind of initial kickoff time will be from 1 to 4 p.m. U.S. Mountain Time, but we'll and we'll be mainly monitoring the Slack channel during that time period. But if you are in say India or France or Morocco, it may make sense. We're not expecting you to change your entire schedule around to participate in the Trustathon. We want you to be able to kind of participate at a more reasonable hour. So whatever that is with your team members, all the material will be made available for you at that time. And the one thing to know with the assignment: once you meet with your team, all the meeting will be conducted through Slack. You should have, for those who are Trustathon participants, you should have gotten a Slack invitation. I've seen everyone providing their introductions in the general channel, so thank you. But the idea is, you will be assigned a problem. If for whatever reason that problem does not appeal to you, you can always choose to go to a different problem. And kind of, we have a lot of discussion questions along the way. We'll provide you a link to we have a Jupyter hub, so it'll be a cloud computing interface where you'll be able to get your own Jupyter instance with either a CPU or you can request a GPU instance. We'll have plenty of memory to load the data and run all the Jupyter notebooks, and then do a lot of you can run the initial code and then do further exploration, and then after you do some exploration on your own with the data and the code and the models, you can meet with your teammates and kind of go through discussion questions and any other things you have found throughout the process. At the end of each day, we want you to kind of we'll have some discussion questions for you that will be on a blog post on our AI2ES website, and from that, we want you in the comments to that. We want one of your team members to reply with kind of the summary of what you're able to discuss and what your answers are, and we're going to kind of compile them throughout the week and sort of see the range of people's responses and thoughts on some of these trustworthiness issues, and what you have found working through the data and thinking about these different users. But at the end of the week, we'll have a final Zoom get together on Thursday, June 30th from 3 to 4 p.m. Mountain Time, where we'll have breakout rooms to have discussions with the organizers. It's not a formal presentation, just a discussion. But you're also welcome to share your thoughts on the Slack in a more asynchronous fashion for those who aren't able to make that particular time frame. And if you have any problems, please let us know in the Slack, in the help channel, and we will try to address those as quickly as possible, especially if there's any issues with the Jupyter Hub or any questions about timing or accessing materials. So we'll send out a more detailed posting of how to access everything, but later today before the Trustathon officially begins. So look forward to that. Next slide. And finally, I want to thank all of the Trustathon organizers. It took a big team to bring this all together for you, and so wanted to call everyone out, especially for our overall organization, Chris Wers, Tasia Peterson, Jennifer Werlow, for particular problems, for Space Weather, Rob Redman, Manoj Nair, Lily Young, for Severe, especially thank Monty Flora and Randy Chase, and for Tropical, Jason Stock, Marie McGraw, Akansha Singh Bansal, Emmett Everett Uphoff, Hamed Alemo Hamad, and Renee Pishki. I'm sorry if I messed up the pronunciation of anyone's names. And I think there are others who have helped out in all the meetings and provided feedback along the way. So thank you so much. I hope you enjoy what we put together and have a very productive experience, learning experience this week. So that'll turn back over to Amy to continue with the other summer school logistics.
Okay, the remaining logistics should be pretty short. So go ahead, next slide. So I want to point this one out. We have a summer school code of conduct. We also have an AI2ES code of conduct, which you're welcome to go see on our website, but they are very similar. We are committed to providing a safe, productive, and welcoming environment for all participants. This summer school code of conduct is being managed, since it's being managed by NCAR and UCAR, it's coming from them. If there are any issues, please contact one of the organizers. You can find me or Tasia or DJ or any of us in the Slack. But we will make sure that we address them very quickly. So you can get to the full code of conduct on the website as well. Next slide. Okay, all the talks are broadcast live. Presumably you're already watching us. They are recorded. They'll be posted as quickly as possible. The Slido, I'm assuming, because what we've done this year is actually really cool. We've integrated the live stream with the Slido directly. So by getting to the live stream, you should already be on Slido. But just in case, you can go to sli.do or slido.com, and you can use the code TAI4ES, or you can scan that QR code. We will remind you of this very regularly because we're going to be doing a bunch of interactive polls during the day, and we want to make sure that you're on Slido actually doing the polls. Everything that you submit on Slido is moderated. This goes with our code of conduct. That way that nothing can come in that violates the code of conduct. So if you submit your question, it will not appear right away, but we have a couple of moderators every single day, and they should be making sure that everything appears quickly. Okay. I think this is just a reminder. We already told you the morning is 9 to 12 Mountain Time. Then there'll be brain breaks in the mornings. Then we're assuming you have a lunch break, and then there's an afternoon, which is 1 to 4 Mountain Time. Again, to address some of the questions that were coming in Slack, you can run the Trustathon at your own time, but the official kickoff is this afternoon. Next slide. If you want to learn more, one of the feedbacks we got last year was, I want to learn more about AI. We're starting with an understanding that you're already going to know what the AI methods are. A lot of so we've had, this is our third year of summer school. DJ ran the first one through NCAR. the first year of the pandemic, 2020. We ran one last year in 2021, and we're doing this one. All of them are archived as well as other short courses that we've provided on our AI2ES.org website. If you go to AI2ES.org and you hit education, and then you get that little pop-up menu, you can get to everything we have available, and you can get to all of that. It'll give you background resources that you may need. Next slide. This one, by the way, will appear there when we're done as well. This is all supported by NSF, and that is our grant number. And I know that he already said thank you to a bunch of people for the Trustathon. I wanted to say thank you very much for NCAR UCAR, because they're running all of this in the background and getting the multimedia team. Tasia Peterson has gotten this all set up, Susan Dubbs at OU, and all of our sponsors and all of our guest speakers and all of you for coming and participating. And with that, I believe the next slide is going to be one quick, go ahead, Chris. There we go. This is also a thank you to all of the people who have agreed to speak. You're going to see all of these people throughout the week. The way we're going to run this so that we don't have introductions for the next 20 minutes is that you're just going to introduce yourself when you start to speak. So I believe with that, we're about to switch to the first speaker for the day. Go ahead. Yes, so I think I've already done my speaking for most of today. I believe the next set of speakers is Ann and Chris. And so with that, or am I doing the next one? Am I doing the agenda? It doesn't matter. Go ahead, since you turned your camera on.
All right. Hello, everyone. My name is Chris Wers. I'm a postdoc working at NCAR on the AI2ES grant that we've just been outlining here. And I study risk communication. So a lot of the stuff I'll be talking about is the social science aspects, and I'll be sharing some insights from the great risk communication team, which also you'll hear from Anne, who co-leads it with Julie Demuth. And then there's Andrea Schumacher, as well as Mariana Keynes, who are involved in that as well. And so that's a team that I represent. And today you're going to hear from some familiar faces, Amy, DJ, and myself and Andrea, as well as Monty, as we're going to cover a couple different topics here. So the goals and objectives for today, we're going to try to cover these in the next couple hours, and we're going to focus on the nature of trust. So that's what I'm going to take over first. And so we talk a lot about trustworthy AI. We're going to unpack what we mean by that and where trust kind of comes from the literature. And then we're also going to be talking about interdisciplinary work, and partially we're talking about that because the Trustathon has a lot of that collaborative and interdisciplinary focus, as well as it's a really important topic for AI2ES. So we're going to make sure we give that a little time, and then we'll dive into more of the meat of things here with the AI side. And that's where we're going to cover evaluation metrics, some of the preliminary XAI methods for evaluation of trust, and how to apply these to your data. And so that agenda comes with, we're pretty close on a little over time on the introductions, but we're going to hit trust first, have a little bit of a break, and then go into interdisciplinary works, and then evaluation and XAI for traditional AML. So with that, what does it mean to trust? So thinking about this from a social science and interdisciplinary perspective, I'm actually going to throw that question back to you all with our first poll. So you'll notice these little yellow boxes happen when we do a poll, which should be going out and live for you to do. And they just correspond to 1.1, the day it is, the number of polls. So when you see this, get ready to go to Slido and take these polls here, and really encourage you to use these opportunities. We put them in pretty strategically throughout. This is your chance to engage with us, to put some insights out there, get your thoughts moving, your chance to speak up in class. And so if you should be able to see that now with the Slido poll out, and we can just get some thoughts rolling. Theoretically, you have some interest in trustworthy AI or some idea of what it means because you came to a summer school based on trust and the Trustathon. So put that in there. Let this fill up a little bit and see what everyone else is saying here. In your own words, what does trustworthy AI mean to you? Got some answers coming in too already. So we have reliable and unbiased, verifiable, physics-based. End users will actually use the AI in high-stakes situations. These are great answers. So learn information from a source that's trustworthy to me, and I will not learn information that's not trustworthy. Meaningful AI results. Great end-to-end. It's not black box. It's understand. It's mechanisms and results. Verifiable. Trusted by the end user. AI is safe and robust and easy to use. These are good. Also, way to engage. Everyone's popping these up. Yeah, unbiased. Interpretable. Physically interpretable. Results are easier to reproduce, less black box. Yep, a lot of key themes we're seeing. So reproducibility, verifiable, and so the people trust it, not black box, explainable, interpretable again. Okay, these are awesome. All right. as I'm gonna let these keep popping in, but we're gonna see a lot of these same words in this next bit of discussion. And so we have this kind of focused on AI, right? So what it means to be trustworthy AI. But we also want to think about trust has a little bit more of a family tree here. So this is something that's been studied for decades in social science literature, like what trust actually is and what it means. And so what I've outlined here is this big family tree is what I'm calling it. And people have studied this in many different lenses. So in the context of organizations, how people work together in teams. And that's been studied in one kind of line of literature, and people have researched that and divided all their little models here, as you can see an example of right below, but also in the sense of automation. So people have been studying, you can see is laid back to like the 80s, thinking about how we trust machines and take over, some of our jobs in these different points. And so that literature is kind of giving the foundation for, what we're doing here in the AI space. Automation is really key, but also game theory. People thought about this as like the prisoner's dilemma, or when you come together and it's like, how do I trust someone else to do what I need them to do or to cooperate? And then also in psychology, there's a lot of different lenses that they've looked at trust, like interpersonal trust and other types of dynamics, as well as some of the risk literature. So looking at about when you focus on a risk or you have some sort of technology that has a risk associated with it, how do you trust different organizations and how does that impact what you're doing? And so this all comes together in this recent trustworthy AI literature, which people have really been trying to tackle and tease out what it means for you to have a really trustworthy model. But what we see is that this is a really, really rich and variable literature. All these different groups of people and really great thoughts have come together over the past decades. And they all highlight slightly different things. Like they emphasize that context really matters. It's different if it's a company that you're trying to trust your boss versus trusting, a partner in like a domestic relationship or something like that. And so when we pull this all together, we define trust for the AI4ES Institute here. We pulled on a couple of different key ideas. The first being that there has to be some sort of willingness to be vulnerable, right? So you don't need to trust if you know exactly what's going to happen. You have to have some sort of this uncertainty here. And then the second point to trust is going to be, we translated this for trying to code it. So we're trying to find this in interview transcripts. So we had to have something that was pretty easy to agree upon, find some consensus around. And we came up with this definition that's a second line too. So when there is uncertainty, it's this degree to which someone does or does not rely on or put faith in something to get a little bit more actionable. And then we also focus on this idea that it's relationship based, between a trustor and a trustee, which brings us to that final definition. Trust is the willingness to assume risk by relying on or believing in the actions of another party. And so with that, we also have some things to think about, because trust is pretty complicated and it really has a lot of context that's associated with it. And so we have these different questions here where we're going to kind of prompt you to be thinking about it. When you say trust, what do we mean? So think about who is being expected to trust. Are you asking, we'll talk a lot about forecasters. So people who are looking and predicting weather, are you asking them to do trust? Are you asking another developer to trust your model? Because those have different implications. They're very different actor types of groups versus if you were asking like a policymaker to trust in your model. And also the targets. So what are they being expected to trust? Are they trusting this AI for like the National Weather Service? Are they using it in the context of making decisions about major severe weather? Or is this something different? We're thinking about your developers or your peers thinking about trusting specific code or something like that. And then also the purpose. So what should they be trusting someone or something for? Is it to make a decision for you? Is it something that's automated, or is it to help you make a decision? That's really going to change the context of trust in this dynamic too. But also the reason of why should we trust something, which gets into trustworthiness. Why are you asking someone to trust a model or to not trust the model in this situation? And also the setting. So the context that the person is in. Are you expecting someone to trust your AI just because you're the teacher and this is a class and they're learning how to do the code, versus trusting them in their professional decision-making? You've given them a tool to aid in this broader process of, say, responding to tornadoes or something like that. So just kind of having these ideas in mind is going to help you think about how the context could change and how context is really important in this space. And so just to synthesize some of the things that we've pulled from this broader literature and that we're seeing in our work so far, is that trust is subjective. And we have this too, where trustworthiness is really going to be in the eye of the beholder. And we saw that a little bit in some of those questions or some of the definitions that came in from the Slido earlier, but it's got to be the end user who thinks it's trustworthy, that I can really rely on something or put a little faith in it. And because this is a really context and what's called value-laden issue, whether or not you trust something, we have to be really careful about making normative or potentially biased statements. Saying you should or should not do these things, because there's a lot of different context and backgrounds and values that could go into this decision. So it's ideas we can work and be collaborative and understand these things, but we shouldn't tell people what to do in some space. And just kind of summarizing the idea is that we're really deciding what's trustworthy for ourselves and not for others in multiple ways. So with that, let's pull it back together. So we've expanded from trust back to trustworthy AI. And what does this really mean for the work that you're going to be doing, what we're going to be doing? And so we know that we have this relational dimension, between someone and something for trust. And it depends on context and has some subjectivity to it. And so what we're going to do is look at some different examples of how end users have thought about trustworthiness and how they're really reflecting about it from some of our work. And so, but before we do that, I want to make sure you also define trustworthiness. And so we have this idea that this is relational. It's also evaluative, right? So you're saying, why should I trust you? Because that's where the trustworthiness component comes in. And so we have the definition down here. So trustworthiness is a truster's evaluation or perception of whether, when, why, or to what degree someone should or should not be trusted. And with that, I'm going to show some data that we have from a recent risk communication related interview process that we've done. And this is really the work of a lot of people at TAI4ES. So I have a lot of shout outs to do here really quick. So this is part of the work that's led by Anne Bostrom, who you'll hear from later, as well as Julie Demuth at NCAR as well. And we've done interviews with the National Weather Service forecasters. And this involved work from Mariana Keynes and Andrew Schumacher, and myself doing these interviews, as well as Julie and Ann, obviously very much involved with different National Weather Service forecasters from across the US. And we're looking specifically at two different products around severe convective weather. So the first one's really going to be, it's the Amanda Burke's product. It all, there's a lot of people to give credit to around hail. And then the Sobash et al. With GJ, who we've heard from, also worked on a lot. And so in this, we talked to 16 forecasters, in different positions in different regions, looking really at their attitudes towards AI and trustworthiness. And some of the themes that we heard here that we're going through, I talked about some of these performance-based metrics is what some of the forecasters talked about when we asked what trustworthiness of guidance or AI products meant to them. And so we hear them talking about the consistency or verification on some parts of it, as well as being able to perform in specific situations. So you see these quotes here from forecaster 4, really wanting to know, how did this technique output verify? How did it look in reality? And then forecaster 5, really looking at how is this performing on a consistent basis? So having a different question of I don't need to know your performance metrics overall, but has it done well continually over time is being really important. And then the same thing too in the bottom one is don't expect it to be perfect, but you need to know that it works well enough, kind of idea. Other major theme we saw from these interviews that we did when talking about trustworthiness was that kind of the relevance and utility of guidance is really important for trustworthiness for these forecasters. And so when you think of that, forecaster 1 talks about, does this product really improve the forecast specifically in terms of timing, location, and intensity? And also too, I see a question in Slido, the numbers represent of our data set, there's 16 forecasters to show you that they're from different people. So forecaster 9 is the 9th person we interviewed. But you'll see that the first person here that we interviewed talked about really needing it to meet a need. If it's trustworthy, then it's going to meet a need. That's what we see. And the same thing too from forecaster 4. It's I need to see have some time to make sure that the guidance is really encompassing the weather we see here. Right, so making sure that this is useful for them. They can really address their specific situation where they're forecasting. The last theme, talking about familiarity and experience with the guidance. So kind of needing some time here. Is I experienced the new guidance with multiple events, my trust would go up as it's doing well, right? So this is something that's built over time. And then know about the guidance's nuances and biases up front. A lot of forecasters talk about you just need to be really transparent here. I need to know where it's going to fail or where it's going to do well, so I can adjust and mentally calibrate for that. And then idea 2, forecaster 10 also talks about the guidance being predictable in its way. So I know what to expect from it. It doesn't just go out to lunch and give me something totally crazy. I have to be able to predict what it's going to do. And so with that, we have a different set of survey items here for you to dig into to think about what trustworthiness means from a model in AI to you all, because we heard kind of what it means from a literature perspective, what some of our end users think from trustworthiness, and now it's your turn to go to Slido and answer this survey questions. There's a good set of them there for you to dig into. So give you time to fill that out. It'll take just a minute or two. And I'll also bring on Anne to help me walk through some of these results as well. Hello, hello. I think we'll have to.
I don't think the poll is open yet, Chris.
Okay. I'm going to push it to live. Or I should ask the tech. There we go. Looks like the first poll is open. There we go. It should be live now. You should be able to take that. There's about 7 questions. So we'll take a little break here. And there's other questions. Feel free to throw them in Slido as well after you're done with the survey. We'll give you some time.
While people are taking it, I will also point out that we have just shared a link to the slides because it's being requested over and over in Slido, and it will go onto the website, but the link has in a comment from myself, Amy.
All right, we got lots of responses coming in so far, about 90. I'm going to test this out, and I wonder if theoretically you should be able to see my screen here. Can you see the results on that?
Yes, it's a little small, but we can see them.
Okay, let's see what I can do about that. How's that look?
Oh, that's much better. Thank you, Chris.
All right. You can let me know how you want to see them too if we want to go through them. But
you want to start, Chris? It looks like we've got strong agreement with the first one here.
Yeah, looks like people agree with us. I'm thinking that it's important to think about the relational or the subjective part of it for sure. That's awesome. Somebody
was listening to what you were saying.
86 somebody's looks like too. Okay, so that's great. Looks like number 2.
Interpretability.
Let's see the whole thing.
Once again, a strong agreement that humans should be able to interpret what the AI model is doing. So it's an interpretable model. And we'll be talking a lot about interpretability as we go forward here. And here we have a little bit more mixed results on that the AI model outputs are accurate, reliable, and reproducible. So they don't sound quite like the forecasters, do they, Chris?
No, not quite the same.
Yeah. Interesting. You want to take this one?
Sure. So when we ask if the AI model has been developed on fair, so findable, accessible, interpretable, and reusable data, we still have a little bit more of a spread. So a good quarter of people are neutral on it, with just over a third agreeing on that, and then 2/3 combined as agreeing or strongly agreeing. So thinking there's some interest in the FAIR principles here. Our audience makes sense.
Which have been widely discussed in the literature.
Yeah.
This is a topic of great importance to AI modelers. The AI model has been tested extensively on relevant out-of-training sample data. And it looks like we have a little bit more agreement. Well, it's about the same. Yeah. Transparency, always a hot topic.
People seem to agree too. That's one of the stronger ones. Transparency is important. All right. Almost half would agree.
Yep, over 60% agreeing or strongly agreeing. Now this is, here we have quite a lot of agreement. Over 50% said agree, and about almost a fifth said strongly agree. So we've got about 78% saying agree or strongly agree. So this is the strongest agreement we've seen of all of these questions. Yeah, that the AI model and its applications are sustainable, socially, and ecologically beneficial. Really interesting to see this. Really important alignment with sustainability goals, for example, in
wonderful
something that we hadn't touched on yet. Yeah.
Yeah, that'll be really cool.
Fascinating. That ties in well with the next section here.
So with this one, we have, just summarizing some of the ideas that we're talking about here, when we're looking at trustworthiness, and Anne and Julie and Mariana are all involved in and Andrea as well, who you're going to hear from in just a minute, and thinking about trustworthiness in this context. You know, what does it really mean? And are we conceptualizing it in a useful and meaningful way? And what we're arguing here is that trustworthiness is more than just about performance. You know, it's not just about, you know, the output that you can decide ahead of time. And it's a subjective evaluation made by the user, right? So we can't just say that the model is trustworthy only to ourselves. We can't say that. We can't just guarantee that it's going to be trustworthy to the end users. And it really depends on the context, you know, so the decision context or how it's used and what's sort of being done with that AI all really, really matter right here. And so with that, we move on to Anne.
Okay, so we saw a lot of discussion of bias in the original definitions that that you all entered. And we can see here that, as David Dank said, there's one reason to desire trust is that it's almost necessary for ethical action that the user has a reasonable belief that the system is going to do what you think it should do, so that it'll behave approximately as intended. And we'll see here in the following and in discussions in the following days that both bias and uncertainty, so error or noise, can cause a system to behave in unintended ways. And so that's problematic. Next, please, Chris. So more broadly, whether an action is ethical or not may depend on either the process or the outcomes of the action. So what the model is doing, what the outcomes of the model are. And there are three different ethical frameworks that we can think about for deciding whether or not an action is ethical. And these are just three of the main ethical frameworks that are used widely. The first is utilitarianism or consequentialism. And that is whether the action is ethical based on whether you think it's useful or it has net benefits to society. So that strong agreement that we saw from all of you that AI should have social benefits, it should be ecologically beneficial, that's a consequentialist perspective. The second framework here is virtue ethics, whether or not something is virtuous or the right thing to do. And people talk about something someone being a good person or being virtuous. That's that kind of a framework. And the third is whether or not it's required by moral principles or duties. And this has the fancy name of deontological ethics. So a key example for both deontological and virtue ethics is of honesty. So people consider honesty a deontological imperative because it respects other people's rights to make their own decision. It respects the autonomy of their will, so free will and free choice. And be honest is also a virtue rule because people think it's virtuous to be honest and that a virtuous person is an honest person. So remember again here that the autonomous and free will and autonomous rights to make decisions are then an deontological imperative and also are aligned with being virtuous. Next slide, please, Chris. So in a paper that Amy McGovern, who you heard from first, led with Emmett Ebert, Uphoff, and DJ and myself, we outline ways in which AI can go wrong for environmental sciences. And there are three different classes of ways they can go wrong that you'll hear a lot about over the next few days. The first are issues related to training data. You can have non-representative training data, for example, lack of geodiversity, so you don't have data from some places. Training labels can be biased or faulty, and also you can have data that's affected by adversaries. I'll show you a quick example of that from the paper. Next, please. There can also be issues related to AI models. So there can be training choices made for the model that can be faulty. The algorithm can learn faulty strategies. AI can learn to fake something plausible. The model can be used in inappropriate situations. And this can especially happen when you don't anticipate what's going to be an inappropriate situation. You could have a non-trustworthy AI model that is deployed, and there may be a lack of robustness of the model. Next, please. And finally, there are more global issues, and this is a non-comprehensive list, but a few examples of this are that, for example, globally applicable AI approaches may stymie burgeoning efforts in developing countries because they're applied from other countries instead. There may be a lack of input or consent on the data collection or model training, and scientists might feel disenfranchised. Finally, there could also be, as has been pointed out in several contexts, an increase of CO2 emissions due to computing. Many of you probably run your models a lot. takes a lot of CPU time. Next, please. So thinking about bias, there's often this kind of a diagram used, and you can see that you have a bias variance trade-off. So you can have low variance and low bias, ideally, but you can have high variance with low bias, or you can have high bias with low variance also. And so this kind of a framework can help you think about this trade-off between bias and variance. Next, please. So different biases can be introduced during model development and employment. Biases can be introduced in problem formulation and research design, data collection, model development, and model deployment. And in the next few slides, we'll discuss 3 forms of bias that can affect AI for environmental sciences. First, computational or model bias, data bias, and decision-making bias. And these are not exhaustive. Bias can be introduced at any point in the algorithmic-driven and assisted decision-making pipeline, from problem specification, where you're figuring out what the problem is, through deploying the model. Next, please. So think of the bias variance decomposition as analogous to regression with squared loss, where 0 bias is what you want to achieve. There's a trade-off between bias and variance, where with machine learning models, lower variance can be achieved if you have higher bias. Approximation is the best we can do with the model we've chosen in our specific hypothesis space. Enlarging the hypothesis class can decrease the approximation error. But the more expressive the class, the lower the approximation error. And bias variance decompositions usually try to decompose this error into 3 terms: the systematic error, the effect of the variance, and the residual or minimal attainable error. The exact decomposition depends on the loss function, L. The most common loss functions are the squared loss for regression problems that you get when you're running a regression model, and the 0-1 loss for classification problems, where you either have identified something as being in a class or not. Inductive bias stems from the way we do the search, so it's broader than just the approximation error. So neural networks can approximate anything, but because we want to generate smooth functions, we get inductive bias as well. So regarding inductive bias, from Mitchell's book on machine learning, the function L of xi and dc notes the classification assigned to the instance xi by L after training on the set of training examples, dc. So next, please. So think of bias variance decomposition is analogous to regression with square trade-off between bias and variance in AI. Models with lower variance can be achieved with higher bias, but it's illustrated here. Data points can be far away from the expected predictions. So you can see the predictions in the solid lines here. And so on the left in figure 37 over here, you can see the bias. This is a figure from Pierre Gertz on bias versus variance decomposition for regression and classification. The source of the error is called bias, and this results from too simple a model, which is essentially independent of the learning set, so the data that you've seen. On the right, the error is attributable to the variability of the model. And in this case, the error is attributable to the variability of the model from one learning set to the other, due to the learning set being sparse, so you have very little data, relative to the complexity of the model, and this is called variance. Next slide, please. So to capture the regularities in a data set, variance misses a lot of assumptions, and it underfits the data. So lowering the prediction bias comes at the cost, however, of increasing the variance of the model prediction. Low bias and high variance, as shown on the right, overfit the data, as it pays way too much attention to the training data, and the prediction variance tends to increase overfitting to the training data. And the bias variance trade-off is going to differ from one learning algorithm to another. Okay, next, please. Next slide, please. Uh-oh. Oh, here it comes. Okay, so here are those examples I was talking about. The example on the upper right shows how even completely unintentionally, biases can emerge in which populations are served by monitoring equipment like weather radars, in which the radar placement results here inadvertently in biases in the data. So you can see that we've got populations here that are not covered by radar, so radar is not in the right places to capture them. And in the lower right, the hail reports come from along highways and cities, biasing the data so that it looks like that's where the hail occurs. Of course, that's where the people are, so that's why they're reporting them there. These are also from the paper that I mentioned by McGovern et al., so that where you can see more detail on these examples. Next, please. Next slide, please. Can you hear me, Chris?
Yep, I just moved ahead. I'm not sure if anyone else can see it, but it should be decision. It might just be a little lagged.
There it is. Yeah, it was just a little lagged. Thank you. Sorry about that. I couldn't tell that you had changed. So heuristics are preferences, and heuristics are rules of thumb that we have in problem solving or making decisions. Sorry, there's a lot of noise here. Can be a source of bias. Biases in problem solving can be described as stemming from how people think, perceive, remember, and represent events and phenomena, so both strategically and by accident or inadvertently, keeping in mind that all of these are extremely context dependent, so much more than most people realize. So, for example, people are likely to perceive motion and color, which are more salient and so stick out more to us than orientation. But orientation also sticks out, so it's the third thing that captures our attention. And people may be limited in their understanding of complexity by working limit memories. So there's this old research called Miller's magical number 7 plus or minus 2, which is the notion that we can only keep a few things in mind at once, and it's a relatively limited capacity. So and so our ability to perceive categories also affects that, because if we can categorize information, we can remember that many categories, and so we can remember a lot more specifics. This can be greatly facilitated by expertise and our understanding of the relationships within the data. So of relevance to understanding that biases, Kahneman has suggested that most common heuristics can be characterized as resulting from attribute substitutions. So we substitute, for example, our feelings often instead or entirely instead of, or in part, instead of our cognitive assessments of what's happening. Sorry about this. And that can happen pretty frequently in the risk context that we're talking about here with regard to weather. So we can also, of course, be affected by systemic biases that stem from the social norms around us and the institutions that we work within. Next, please. So my last slide here is just a reminder that there are ethical frameworks being developed around the world here, and this is an example from the high-level expert group, or HLEG, on AI in the European Commission that was developing a framework that includes 4 ethics principles, and it includes some of the ethics principles that we just talked about, notably the respect for human autonomy and the right to make your own decisions, but also the prevention of harm, the notion of fairness, and importantly for this group, explicability. And note also that the social and environmental well-being that all of you highlighted as being really important, and which would be dictated by utilitarian ethics, is included under the 7 key responsibilities within the framework. And I think that's it for me, Chris.
Yes, great. So we're a little bit behind schedule by 10 minutes, but Andrea has offered up a few minutes of her schedule. So we should, I don't know, Andrea, can you handle 10 minutes faster? If we still have time for a break, or do you want to cut the break?
Do 5 minutes faster, and we'll cut 5 out of the later stuff too.
Okay, sounds good. So do you want to take a break now?
5-minute break, I think sounds good to give us a chance to get Andrea in here. So tell everybody we'll be back in at 11:55 instead of 9:45. I'm sorry, I'm in the East Coast. 9:55.
Yes. I'll update it on here too. So everyone, you get a 5-minute break for now. We'll come back in 5.
Thanks, Chris.
Okay, well, thank you for coming on back from the break. And so now we're going to shift gears just a little bit and talk about insights on meaningful interdisciplinary work, particularly in the AI and machine learning development process. I'll introduce myself. I'm Andrea Schumacher. I am a researcher at Colorado State University at the Cooperative Institute, CIRA, and I help develop tropical cyclone products and have been working very much in the interdisciplinary space and working on societal impacts of tropical cyclones for several years now. So next slide. So I kind of wanted to start us off on a bit of a light note. There's this saying that's attributed to Sir Alec Isagonis. I actually heard it on the show Parks and Recreation. That is, a camel is a horse designed by committee. And I thought that was a really interesting idea and sort of applicable to the idea of interdisciplinary research, because we could substitute committee for, maybe we should call this a not ideal interdisciplinary research team. With the idea being that sometimes when you get lots of different people together with their own interests, their own specialties, their own goals, to do one common goal, if there isn't a lot of cross communication, aligning of methods of goals, you can end up with something that really does not look like what you were hoping to. You might end up with a camel. And so hopefully, I'm just going to give you a few tips during this section to help you not make too many camels in your future, particularly with your AI interdisciplinary work. So I wanted to pause here and put up a Slido poll, just asking you all to give me some terms that you think of when you think of good or effective interdisciplinary research. And I'll give you 30 seconds to a minute to throw up some suggestions. So I've got a note just from DJ on one answer about basically sharing and versioning, like Figshare and Zenodo, if you want to share something. That's very important. Whoa. Oh, awesome. Collaborative collaboration. I love that. Synergy, no boundaries. Exactly. Mutually informed is really great too. That's something we'll talk about. And simple and so I like, there's kind of a mixture of keeping things simple, but also tackling complex problems, it seems like here, which is kind of a perfect encapsulation of what I'm hoping to talk about. And thanks, Chris, this is awesome. Okay, so maybe let's move on, and I'll tell you what I think are some of the most important terms. I'm certainly not the expert in this, but hopefully I can help share, particularly with some things we've learned through the AI risk communication work. So, what does it mean to do interdisciplinary work? Is the screen? Okay, awesome. So we have unidisciplinary work, which is just a single discipline. And then we have multidisciplinary work, which is, of course, multiple different disciplines. We all get together and we want to maybe attack a common problem. So I'm sorry, something happened with my screen. And my screen is so small now. There it is. Fabulous. Okay, so next slide. Sorry about that. So we talk about interdisciplinary work. We're talking about work that integrates information, data, methods, tools, concepts, theories from two or more disciplines focused on a complex question, problem, topic, or theme. So we're all trying to solve the same complicated problem, and we're going to, instead of working on it separately and talking about it after the fact, we're going to integrate everything, hopefully from the beginning. That's really when you get the most success. So the key defining concept for interdisciplinary work is integration. So a blending of diverse inputs that differ from and is more than the sum of the parts. So we've always heard that nice saying about the sum total of the parts is greater than the individual. So we're looking for something where we're layering, we're working together at each step in order to tackle these problems. And I will note there is another term you may hear called transdisciplinary, which really involves a lot more. All these blocks would be sort of scattered around. So that is like one step further. We're really looking to make big paradigm shifts, and we're working together to create new concepts and methods. So next slide. So when you're planning this work, you want to ask sometimes a little tough questions, like, would the project totally fall apart if one discipline dropped out? That's a pretty good indication of if everybody is actually fully invested in a way that's going to lead you to good interdisciplinary outcomes. And how do we make the leap from multidisciplinary, where everybody is doing the things that they're most comfortable with, to interdisciplinary, where we're all layering on each other in order to create something that's better than the sum of all our individual parts. Next. So for the Trustathon this week, we want you to keep these things in mind. So are you really listening to and meaningfully integrating each team member's perspective? That's a really important one, really hard to do sometimes, but it is key and involves a lot of opening up our listening ears. And is your work really the sum of all parts? Once again, are you making something that's better than you can do individually? So next slide. So I just wanted to go through the interdisciplinary risk communication research approach that we've been using here at the AI Institute. And we have these interdisciplinary research teams working together. They involve scientists from risk communication, environmental and atmospheric scientists, and AI and machine learning scientists and developers. And they're all working on these different aspects, which includes users, understanding our users and decision makers. That's a key concept with a lot of AI work. We're making things for other people to use. And so our users are diverse, including the National Weather Service, USGS, a lot of government agencies, even private entities. So understanding all of these user groups is really, really key for all groups really to understand. The AI scientists may be and machine learning techniques to create the best predictions with the highest skill possible. And we also have social scientists doing data collection with methods such as formative research, which includes semi-structured interviews, randomized experiments, and evaluative research, which includes surveys in naturalistic settings. And this is, once again, working with the users to really understand their needs, their workflow, so that we can maximize the AI ML techniques and their use over time. And so all of this comes into this process of trustworthy and use-driven AI and machine learning products. We're really hoping to create products that are what the users want and need, and also maximize their ability to fit into their workflow. So next slide. So I'm going to discuss a couple of results from this paper by Morse et al. On the within interdisciplinary research, and I'm share some of their key insights on meaningful interdisciplinary work in the AI ML development process, and show you some real examples from our work. So first of all, interdisciplinary research incorporates full intellectual participation by each contributing area of expertise, forming a multi-way partnership. We'll get into an example that will hopefully help with that. Generates novel research questions, approaches, and interpretations, and provides rigorous, useful new insights about a complex intellectual and/or societal problem. So, next. So we'll start with that first goal, which was incorporating full intellectual participation by each contributing area of expertise, and creating this really rich multi-way partnership. So in this example, we're going to talk about communicating values, so for the space and for the research. So this is an example from our Tropical Cyclone Working Group, which is working with the Tropical Cyclone AI Group and the risk communication scientists. And the first, I'm just going to we're still early in this research, but I want to go through the first steps. A lot of this actually involves putting a lot of time in up front so that everybody is fully intellectually participating, communicating values both for the space and for the research. That includes ideas about transparency, respect, enthusiasm, giving all the time to everyone to speak and think and really work through these problems together. So we have these common goals. Talking about our different disciplines and experiences and expertise, and to really communicate to and with each other. And I have just a quick little slide there, but let's go on to the next slide. So I sort of made this graphic to show sort of how we've attacked this. So we have a group of risk communication researchers, and we have a group of product developers who work in AI and tropical cyclone forecast product development. And we have honestly spent our first 2 to 3 meetings together, really just talking about our individual group goals, methods, timelines, giving examples of past work, particularly the work that's most relevant, and really just trying to get a common ground where we understand each other and we understand each other's goals and our restrictions. For instance, the Tropical Cyclone Group has actually worked with forecasters for a very long time at the National Hurricane Center, has developed some really good relationships. And so understanding those relationships and making sure that this research can leverage those relationships, but also respect those relationships and the boundaries therein was a really important part of this process. And so we work together, and we're at the point of defining mutual goals for our current products that we'd like to develop and to demonstrate. A lot of issues came up, of course, with terminology and vocabulary. That's really something that's key in interdisciplinary work. A lot of the time, words that mean one thing in one discipline might mean something completely different, or even just slightly different, which is almost worse in another discipline. And then talking about existing relationships with users, as I said, and those limitations. And so in the end, we have a set of common goals, timelines that are all of mutual benefit to both of our groups. And this is really key too, because everybody has to be getting something out of this. Sometimes the scientific process sort of shortchanges one side or the other, but to do really good interdisciplinary research, everybody has to be getting their needs met from a research standpoint. So next slide. Okay, so our other goal, our second goal, was to generate novel research questions. This is a point where I'm actually going to turn it back over to Chris for a few minutes, because he was one of the key figures in this really cool application or meeting of this goal. So.
Thanks, Andrea. So this example comes from the Winter Working Group. So this is a collaboration with a lot of people from the University of Albany who are involved in AI4ES, along with the risk communication team I mentioned, give a lot of shout outs and who you've heard a lot from so far today. And the key idea here is you need to do something new, right? So when you come together, you should be stronger. Andrea's done a really good job of highlighting that. An example here is that we've used these methods from communication research. It's called content analysis. That's been used for a long, long time in communication research for getting at things like studying news media. So first it began by looking at media articles. Can we find things reliably, like trust? Can we see these different types of themes here? But we don't have any AI for that back at the time. So to think about how to train people consistently, can we get you kind of intercoder reliability, which means that me and a team of 4 people could apply the same labeling scheme like you would do in supervised learning across a big set of media. And so we'd learn how to do that consistently following a code book. We had stats, they have called Cryptonorth Alpha for making sure we do it reliably and controlling for chance, and would do that very, very commonly. And so actually Julie Demuth was working with a project that had some supervised machine learning. It's like, hey, you're doing content analysis. This is a method we have tools for. How are you looking and thinking about it? And since that, following that idea, we've worked with New York State Mesonet images, which you can see in the bottom right, to develop a human coding scheme. So there's the 4 of us. So Vanessa's leading this project at University of Albany, and we're working with Carly and Mariana, and being able to code thousands of images for the supervised model to be able to predict whether or not or essentially detect precipitation streaks, like you can see in the bottom at night. And so we have this code book, several pages of this is what it means when there's precipitation, when it's not precipitation, when there's obstructions, like spider webs you can see on the bottom right-hand side. And then Vanessa used those codings to train an algorithm. The idea being, hopefully we can use this approach to make it more trustworthy. So there's human involvement, but we also kind of have this consistent idea we know what we're doing. And so it's a new technique really developed out of needing the merging the minds. You need both the really strong knowledge of AI, but also the content analysis communication side come together in one project. I'll hand it back to Andrea.
Thanks, Chris. So yeah, that's such an awesome example of, they had really good interdisciplinary conversations and methods going in order to make this kind of knowledge share. Otherwise, this just honestly may not have happened. So thanks for talking about that, Chris. So the third goal from the Morse et al. Paper was to provide rigorous, useful new insights about a complex intellectual and/or societal problem. So the key words here I see are rigorous insights about a complex problem. And so an example, a really great example from our TAI4ES work is some of the products that have been developed for severe weather forecasters. And so AI, meteorology, and risk communication experts in this case have come together to help address needs and challenges faced by the National Weather Service forecasters, particularly for severe weather here. And this work requires deep integration of expertise and experience to better understand a complex and time-constrained decision-making context. And so I just wanted to talk about briefly this idea of complex. I think it's really exemplified when we look at the National Weather Service and real-time forecaster problems. So we have this new AI product. We have someone who knows enough about the Weather Service and what their needs are, and also what they can do with AI and machine learning techniques. And they create some great AI product that's going to predict something about severe weather. In this case, one real example might be the types of storm phase or hail prediction. So next slide. We'll show a little more of the context that we're looking at. So in a forecast office, forecasters often have, I think I counted 8 screens open at a time. And the AI is going to product, if it's something that the forecaster needs and wants to look at, is going to have to, regardless, is going to be fighting for real estate on those screens. So there's a bigger context as forecasters are looking at radar, satellite, so remote observations. They're looking at model outcomes. They're looking sometimes at webcam data, sort of for situational awareness. They're also oftentimes monitoring social media. And so in this is a very complex process. AI sort of has to fit in. And if we don't know what the complex process is, we might just be throwing something, we're throwing spaghetti at the wall and hoping it sticks, versus doing something deliberate and collaborative that's going to hopefully ensure success. Next slide. So in addition to the forecast office, which is already complex, these risk messages about severe weather go through other communicators, such as broadcast meteorologists, sometimes emergency managers also, depending on the type of risk. And so once again, we have another layer to what this AI product is going to be doing. It's a multi-step process that it's going to be influencing. So it's very good to know what you're looking at beforehand. Next slide, sorry. And then finally, we're looking at consequences, that impacts. That just adds another complexity, because ultimately what we're trying to do is avoid, to whatever extent possible, any sort of negative impacts from these events, particularly in ensuring that we don't see loss of life, and to whatever extent possible, destruction of property. So it's not just a one single complex problem within one station even. It's something that is propagating through an entire communication system. And it really behooves us to understand this complex situation when we're working in interdisciplinary spaces, so that and that's really the benefit of interdisciplinary work, is we have the tools, a lot of the time, to understand all of these different steps. So Next slide. So I just wanted to finish off with leaving you with just, I try to get a little more in depth on some of these issues, but we can also just sort of give you some broad best practices for interdisciplinary research. You all had such great ideas already at the beginning that I'm sure that you could add to this, but this is just a summary from, I believe it's the University of Maryland, Baltimore County. They actually had a really nice summary that I thought I would throw up here. So best practices are starting with the problem always. The problem is something which no single discipline has been able to resolve. So this is where we need interdisciplinary collaboration in order to solve these big problems. And make sure each collaborator understands how the problem involves their area of research. So once again, making sure everybody is aligned and invested. Build your team. It's good to have people who can play key roles. This is always just a good idea, whether you're doing interdisciplinary research or not. But in particular, having people maybe who are good at visionary, mediating, facilitating, technically strong, making sure your team is rounded out so you have all the skills represented that you're going to need to work on this research problem. Take time to learn the lingo. Like I said, a lot of words mean the same thing in different disciplines, or they mean completely different things, or they're just a little bit off. There's a lot of language that we need to get straight a lot of the time before we can actually make good progress and be efficient at communicating with each other. So it's worth taking time and investing and working through this step as much as you can early on. I'm going to also tweak that a little and say it's not just words. A lot of the time it's data. I've done a lot of work with the epidemiology community, and there are such key distinctions that really sometimes seem insurmountable in terms of the data and the software we use and how different they are. They use smaller data sets a lot of the time, and so their data is in like CSV format, whereas a lot of the atmospheric data we have are in huge terabytes and terabytes of data. So we have to use software like Fortran in order to efficiently read and work with that data, whereas they are much more comfortable with R. So anyways, it's not just verbal communication, it also has to do with technical communication as well. Be flexible and don't assume anything. So take time, as I said early on, to have everyone describe the project for the team as they would explain it to an outsider and say what they hope to get out of the project. Don't assume that the other people just see what is important to you about this project. It's really good to uncover these conceptual disconnects as early as possible. Just a note about publications. Different disciplines publish in different journals, and so it's really good to kind of get that hashed out at the beginning too, and where your sites are, just so that you have a clear idea of who's going to be doing what and what publications are going to be handled by the group. And a history of working together. This is sort of my favorite. All the interdisciplinary researchers I've come to work with, I've met through conferences or through workshops, and these are people that I've slowly started collecting, these people that I think would be great to work with, and that's where you can start pulling from when you have these new project ideas. You can sort of start thinking about your mental Rolodex of your team. So even brief periods of collaboration prior to submitting proposals can help you figure out whether this is someone that you can really work with, that you can work together. Because like I said, there's a lot to it in the early stages, and you want to make sure you're working with someone who is like-minded in terms of the rigor that you plan to put into this project, into the interdisciplinary process. So pull from the bench as much as you can. So, and I think that's it. And I think I'll skip the Slido here. I'd be happy to answer any questions, but I will turn it over, I believe, to Anne and Chris.
Great. Yeah, I'm happy to take the next slide then. Thank you, Andrea. So we just wanted to highlight, and maybe we'll save a little time here, that there are standards being developed for trustworthy AI around the world, as mentioned in the previous section. Here are 3 examples. There's an executive order here from the US President Biden, looking to ensure that technical standards reflect federal priorities for innovation, public trust, and public confidence in systems that use AI technologies. And this was issued in 2019 and has paved the way for AI institutes, such as the one that we are part of AI2ES. The second here is an example from the National Institute of Standards and Technology, and it's a plan that's being developed in response to the executive order on trustworthiness standards, including guidance and requirements for accuracy, explainability, resiliency, safety, reliability, objectivity, and security. And the third here is from the International Organization for Standardization. It's an ISO standard for the international stage, and you can see here highlighted in this ISO standard characteristics of trustworthiness that include reliability, availability, resilience, security, privacy, safety, accountability. Also, transparency here again, quality, and usability. Next, please. So we wanted to highlight here, this is a format for thinking about the different levels of organization of how we think about what influences trustworthiness and trust and risk perception. In particular, and this is from Ortwin Wren's work. And you can see here that we've put an arrow from these standards into socio-political institutions. If you think about this from the individual with individual risk perception, which is right here at the core of this diagram, and individuals process information and use rules of thumb and heuristics and their emotions instead of their cognition sometimes. We also use our common sense to make sense and interpret what's going on. When we go to higher factors here, we can think about that there are interactions between our beliefs and our emotions and cognitions, and we move all the way up to socio-political institutions here, the institutions that we operate within, like, for example, the International Organizers for Standardization. Those influence the entire environment in which we work. And beyond that, we have cultural backgrounds, all of us, that influence and collective influences on our own understanding and actions within the AI space and within the space of trustworthy AI. But we can look also at this arrow here and think about the contrast between what happens at this more standardized level, this more formalized level, and what happens at the individual level, where, as Chris pointed out, trust is actually, and trustworthiness are actually individual perceptions. And sometimes there can be conflicts between the more formalized way of thinking about them, which is general at the socio-political level, and the individual level. And there can also be contrasting understandings here that can be somewhat difficult to navigate, where the standards recognize that trustworthiness is also very context specific, but standards by their nature are general and try to apply across a set of different contexts. And you can get discrepancies between what people think should be happening in a specific context, a specific AI application context, for example, for severe weather, and what is labeled as part of the standard at a more general level that may not be applicable in a very specific contextual level. So it's important to think about the fact that trustworthiness is highly contextual and may be interpreted differently by each of us, but it also is subject to these very high-level socio-political institutional standards, which are generalized and attempt to apply across many different contexts and conditions. Thank you.
All right, and with that, we're perfectly back on schedule. We'll get an extra 1 minute for the 5-minute break here. So we'll see you again at 10:30 for the second part. So in 6 minutes.
Well, it's still right before noon here, but good morning, afternoon, nighttime, wherever you're at. I'm Dr. Montgomery Flora. I'm a postdoc at the University of Oklahoma, working at the National Weather Center. I do research in developing AI and machine learning techniques for short-term severe weather forecasting, but I also have a fair bit of expertise in model verification and machine learning explainability techniques. So what we're going to be talking about, we're going to be kind of switching course quite a bit, and we're going to be kind of talking about first order explainability, which is kind of verifying that your model actually works. So what makes a machine learning model good? So a key component to machine learning development is evaluating our model's performance, but what makes the model good? Back in the early 90s, Alan Murphy, which is kind of the pioneer for model verification, especially within weather forecasting, kind of came up with 3 indications. And this kind of ties back into some of the talks we were talking about earlier. So first is kind of consistency. We want to see the degree to which our forecast or our prediction is corresponding with the forecaster's judgment or our end user's judgment about the situation based on their knowledge of the situation. The quality then is going to be the degree to which like the forecast or the prediction actually occurred, corresponds with what happened. And then the value is the degree to which our forecaster or our end user is actually finding this useful as a decision maker to realize some kind of incremental economic or other benefit. What I'll be mainly talking about is stuff that we can kind of quantify much more easier. It can be very difficult without conferring with your end users to figure out what consistency and value are, but we can use, so typically when we're verifying our model, we're usually just starting off with quality. So can we use just one statistic to describe our prediction quality? And the answer is simply no. Our prediction errors, our model errors are going to be just like any other random variable, and it requires a full distribution to describe it. Because you can imagine that we might want to ask some of the following questions, what was the average difference between our prediction and our target? Say our mean square error of rainfall prediction is half an inch or a quarter of an inch. Was the predicted magnitude correct? Was our prediction biased? Maybe we are able to get the observed rainfall distribution correct, but maybe we're a quarter of an inch too big in most cases. How often does the model kind of like totally fail? And we may want to ask questions like that. Did we get the timing correctly? So we really can't summarize this with one number. We really need a lot of different numbers to help us understand how well these models are performing. So before we kind of jump into things, we figured we'd kind of set up a quick little poll to ask about your familiarity with these different verification diagrams, which are ways to kind of summarize multiple verification statistics. So I'll let Chris or whoever kind of get that going. Well, here we go. Okay, now we have some results. Okay, so yeah, we'll be talking about various different diagrams. So it seems like with the rock diagram, about a third of you are not familiar at all, and that's fine. But we also do see a third are also very, very familiar with it, moderately to extremely familiar with it. Much less familiar with the reliability diagram. That one is, as I said, that unfortunately that one doesn't really come up a lot in machine learning courses, so there's no surprise there. Now, yeah, okay. This one, yeah, is becoming a little bit more popular, but it makes sense why that one would be a little less familiar. This one I definitely expected. This one, it's unfortunate that it's not more common because it's probably one of the only verification diagrams for regression tasks. So I think these results make quite a bit of sense. So we'll definitely take that into account as we go through these slides. Do I need to reshare my screen?
Yes.
Okay. Okay. So, like I said, really, what we want to do, because I argue that we need multiple statistics. It's really helpful to kind of see the relationship between these statistics, not just see them, plotted in a table. But is there a way we can kind of visualize this that's helpful not only for ourselves as developers, but also for our end users as well? So kind of jumping into things, when we're doing classification prediction, so we're trying to predict like, say, yes, no, or is this a cat or a dog or something like that, we have the ability to issue either deterministic predictions or probabilistic predictions. So let's say we're dealing with like something that has a binary outcome. It's a yes, no. Did the tornado happen? Did the tornado not happen? We can issue also a yes or no forecast, or we can issue something, we can issue these frequencies between 0 and 1 that we would interpret as a probability. So say 70% chance of the tornado or 20% chance. when we're doing the binary prediction and the binary outcome, we can build a contingency table like this. So in this case, let's say we predict yes. So yes, there'll be a tornado, and the outcome is also yes. Then that's what in the meteorological world, we'll call that a hit. We've hit it. Whereas, let's say, for example, I predict yes, the tornado will happen, but the outcome is no. Then that's an indication of a false alarm. Now you'll see here that I have quite a different couple names for these. Unfortunately, the naming convention is not going to be consistent across different domains. Where instead of hit, you might see the term true positive. And, if you're talking about miss, you might see miss or false negative or type 2 error. These are all talking about the exact same thing, but unfortunately, there's different names for them. So we really need to think, more deeply about our model performance and our end user. So a perfect prediction or a perfect model in terms of classification will only produce hits and correct negatives. It'll have no misses or false alarms. But for most tasks, in reality, models have errors, and so our predictions will have some amount of misses and some amount of false alarms. So our main goal then is to try and either limit both of them or realistically, in most cases, try and strike a balance between them. And so the decision on how to balance misses with false alarms is a decision that you ought to be making in conjunction with your end user. For example, you may have a forecaster who is much more concerned about limiting misses. So they're okay with perhaps issuing more false alarms if it means that they're not missing an event, which might mean getting guidance out to somebody that could save life or reduce, property damages or something like that. Once we have that contingency table, the 4 values, we can actually compute several statistics from that. And this is a non-exhaustive list, but we can look at something like probability of detection, which kind of says, okay, if a tornado happens, what's the likelihood that I'm going to forecast that correctly? And there's a variety of different things. You have like this critical success index, which is basically, it looks like accuracy. So the amount that you predicted correctly over the total amount, but in this case, you're not including correct negatives, which is when you say it's not going to happen and the event didn't happen. And when we're doing like rare event forecasting, we may not be so concerned with that. So that's it's good to not include that in the denominator, which might give us a false impression of how well we're doing. And yet again, because these things got developed at similar times in different disciplines, they may have different names. So depending on what field you're coming from, you may call probability of detection something quite differently. It could be the true positive rate or recall, so on and so forth. So when we have these probabilities, when we make like a probabilistic prediction, like say we predicted that there would be an 80% chance of rainfall exceeding 2 inches, then to be able to evaluate it against our binary outcome, we have to convert our probabilities to a binary prediction using some threshold. So in this case, we may pick a threshold of like 0.5 and convert our probabilities into yes and no forecasts. And from there, then we can create the 4 regions of the contingency table, the correct negatives, the hits, the misses, and the false alarms. So jumping into it, I think we said that we were most familiar with the rock diagram, so I'll try and go through this one a little bit quicker. The rock diagram or the rock curve is trying to measure how well these probabilities are discriminating between event and non-event. So realistically, what you're thinking here is how well are we separating the red region, which is where our probabilities are associated with no event, and our green region is our probabilities that are associated with, yes, the event happened. So we really want to see those 2 regions being as far apart from each other as possible. That indicates that our probabilities are really able to distinguish between when event will happen and when event will not happen. So basically, to create the rock diagram, we'll take a series of probability thresholds from, say, 0 to 100, and we're going to compute the POD, so the proportion of the observed yes that was hit, and our POFT, the probability of false detection, which is the proportion of where an event didn't happen, but we had a false alarm. And so if our probabilities are discriminating well between event and non-event, then the POD should increase much faster than the POFT, as the threshold increases. But you can have situations where the POD will equal the POFT for all thresholds, and that's going to create that dashed line that you see there, which indicates that your model has no discrimination ability whatsoever. It cannot distinguish between events and non-events. Now, usually you may see this full curve on this diagram, but sometimes we may just want to summarize it. So if we take the area under that curve, then that kind of helps us summarize this diagram. So if you were along that dashed, the area under this is obviously 0.5. And then the closer that we can get to 1, which is the curve basically hugged the upper left hand corner, then that would indicate perfect discrimination. As a complementary diagram to that is the performance diagram. So one of the key issues with the ROC diagram is that it measures how well we're discriminating between event and non-event equally. But there can be situations where the task at hand really calls for us to predict the event much more skillfully than the non-event. So if we're doing something like rare event forecasting, so if you have rare extreme temperatures or tornadoes, then we're much more concerned with our ability to predict the event than we are with trying to predict the non-event. And that's what this diagram is attempting to capture by looking at how well we can balance hits with false alarms. So a model that is balancing hits and false alarms really well is going to have a maximum CSI, which I described a couple slides ago. That's what's being shown here in the colored contours. It'll have a maximum CSI as close to 1, also being associated with a frequency bias close to 1. So you can see here that CSI has a very nonlinear relationship with hits and false alarms. I can get the same CSI here as here. So what this means is that I could over forecast a whole lot. I could basically say yes on everything, in which case I'm going to actually do really good at hitting the event, but I'm going to have a lot of false alarms. Vice versa, I could say no all the time, and in which case I won't have any false alarms, but I'll never hit the event. So we really want to make sure that we're not doing what's called forecast hedging or prediction hedging, where we're trying to bias our performance by doing one of these bad behaviors. And then lastly, this curve, so like much like that one where you had the dashed diagonal, what indicates very bad performance in this case is any curve that lies along that vertical dash line, which, if you're curious, is equal to the event rate of your data set. So if like 10% of your data set is tornadoes, then that's what this line would indicate. Like, or in this case, you say 20% of your data was tornado, 80% was not, then that's what this dashed line indicates. And likewise, similar to the ROC diagram, we can summarize this curve based on the area underlying this curve to the origin, which is very useful, kind of give you like a first glance, you know, how well your model, again, is balancing hits with false alarms. So this was a diagram that most of the participants said that they were unfamiliar with. So when we're issuing probabilities, when we're basically issuing these frequencies between 0 and 1, we want to actually make sure that they're probabilities. And what that means is, if I say something's going to happen with a 20% chance, then hopefully over a long period of time, the event happens 20% of the time. If it doesn't, then I don't actually have probabilities. And so what we're trying to measure with a diagram like this is to see that you actually have probabilities and that they are reliable. So what we do is take our forecast probabilities and obviously match it up to our binary outcomes. And then we're going to bin them and compute the mean forecast probability, say in one of these bins, and then the conditional event frequency. So to think about it, let's take the bin from 10 to 20%. So we're going to take all of our probabilities that were in the 10 to 20% range and compute the average probability. Hopefully it's equal to whatever the average should be here, so like 15%. And then those probabilities were associated with like a 1 or a 0. And so you're going to take all those 1s and 0s, add them up together, and divide by the total number. And that's going to kind of give you like your, what we call the conditional event frequency in that bin. ideally, that value should also equal, say, 15%. And the more that those mean frequency, or your probabilities from your system actually match these conditional event frequencies, the more reliable your system is. So you really want to be lying along that dashed line. And then any indication of how far you are away from that dashed line indicates where your system may be suffering from reliability. So in this case, we can see the line is falling below. So in this case, we have a mean forecast probability of like, 70%, or 80%, sorry. So we have a mean forecast probability of 80%, sorry, whereas the observed frequency is 70%. So our system's overconfident. So it's that probability should be closer to 70. So it indicates that our system's a little bit overconfident for higher probabilities. There are some additional other information being shown on this, but I don't have time to go into that today. I do have actually a slides that I gave for AI4ES that goes into a little bit more detail of what all these other things are. So I definitely recommend you checking that out on the AI4ES website. So all those three previous diagrams are the most common diagrams when it comes to measuring a classification system. But there's very few diagrams that I know of that summarize multiple statistics for a regression test, like if you're trying to predict the amount of rainfall, as opposed to whether or not it'll be like greater than an inch or not. So this diagram is going to be showing you several statistics. The first is what is called the bias corrected or centered Rmse. So this is the Rmse that doesn't have bias in it. And that's measured as the radial distance. So from, say, the star outward, that is what's being measured there. You're also looking at the standard deviation. So we really want the spread of our forecast to measure the true variance of our system. We're also measuring correlation coefficient. So ideally, for example, our predicted amount of rainfall should have a linear relationship with the true amount of rainfall. And that's being measured as the angle from the origin, where a larger angle would indicate lower correlation. And then lastly, the color coding of, say, the dots here indicate your bias. So you're kind of like your average distance, the average difference between your prediction and the average of the target variable. So in this case, what would indicate like a perfect model is lining basically on this star. You have a correlation coefficient of 1. The prediction variance matches your target variance, and then you have an Rmse of 0. And then ideally, you also want that bias to be near 0 as well. Like for this, so in like this particular case, the purple would indicate that we have like a large negative bias. So I don't know where we're at on time. So I don't know if we're going to be jumping in with Amy for the
you're ahead of time. So I would say let's pause very briefly and ask for any questions, because that was a short introduction to a lot of evaluation metrics. So let's do a pause before we hop into the traditional ML.
Okay.
Especially for those who want to maybe go back to the Taylor diagram, because I suspect there might be questions on that, since it was the one that was most unfamiliar to people.
Okay. Yeah. And if there are questions, you'll have to like say them aloud. I don't know if I have access to like.
Okay, if they show up in the Slido, I can read them to you.
Okay.
We'll give it, because the live stream is 30 seconds behind, and then the questions have to get moderated, so we'll give it a minute or so here.
Okay.
We have one question from Christina Kumler. She says, please go back to the Taylor diagram and explain what a more normal regression analysis would look like as opposed to a perfect. What would change?
Oh, so basically kind of like comparing. So these these dots on here indicate like where your performance would lie. So like if I was interpreting this, so I think, what is it? One of them is a random forest. Sorry. One of them is like a random forest or a gradient boosted tree. And I think you actually see this same diagram on the Trustathon. So this was trying to measure like amount of lightning flashes. So like a couple of the takeaways here is that we have an RMSE or a centered RMSE of about 125. So we know that on average, we're missing the truth on average by about 125 flashes. We're also low. If you see this dashed line here, that's where the true variance of the prediction is. So we're also under predicting the true amount of variance. So our machine learning model is not capturing the full variance of the target variable. So it's probably tending to be biased in that way. So it's not going to be trying to, so that may mean that it's not going to be robust in a lot of different situations. It may be prone to giving kind of the exact same prediction in too many situations, and therefore the robustness of it is going to go down. And then lastly, like I said, we can see that we're purple. So that indicates that we have a strong negative bias. So not only do we have that RMSE, but in general, it seems like we're on average about, what is that, negative 16 flashes short of where the target variable average is. So our distribution is shifted lower, and basically the overall indication here, and then the last one here is the correlation coefficient. So we're at about 0.8. So it means we have a decent linear correlation. And unfortunately, you'll have to see this when you go into the Trustathon. You'll see that basically the model's not doing a great job of predicting really large amount of lightning flashes. And that's why the linear correlation is not better. I hope that answers. I hope I didn't go on like a weird tangent.
There are a couple more questions that I think are related. And
okay.
Christina can type back on hers if she needs to ask for more. And so one from Seth McGinnis asking what's non-centered RMSE, and then there's another one that's related from Sunglin Heish, which I probably mangled and I'm sorry, that asks how to determine the standard deviation of the RMSE. So I think those are two related questions.
Okay. Yeah, so I'm guessing the standard deviation of the RMSE is basically like if you wanted to do like your uncertainty, like if you wanted to put error bars on this.
Right. Well, I think they're both asking about how you did the RMSE in here. So how you did the centered RMSE, and then how you know that you're below and above.
My memory may be failing me. So if you're familiar, so RMSE, or like if you're familiar with Breyer's skill score or Breyer's score, you can decompose these error terms, kind of like what Anne was talking about, where you can decompose like variance into different terms. And so mean squared error can be decomposed into different components. And so there's basically the like true RMS, or this true mean squared error. And then there's this mean squared error that you get from bias, basically from your model having bias. So it may not be the best indication of how bad your model's performing. And so you can take that component out of it. So it ends up giving you a better representation of what the true mean squared error is. And offhand, I don't know the exact decomposition, but it's basically a way of decomposing that position into different terms. And the centered RMSE is the only one that actually works out for this diagram. You wouldn't be able to show the full RMSE on this diagram, unfortunately.
Okay, there are a few more coming in, and I'm trying to do that plus mute and unmute myself. Another one asking about the Taylor diagram. Is it suitable for both supervised and unsupervised machine learning?
I think it's suitable for any regression task. If you're doing any type of regression task, so if you're doing like an unsupervised learning and you're trying to like measure how well your like k-means, like a k-means neighborhood is working. As long as you feel that you can use any one of these statistics for the problem at hand, I would say yes. So if you're trying to measure, much like a regression task, as long as it fits in that paradigm, then you can totally use this diagram.
Okay, and I have one more related question, and then I'm gonna it'll be my turn because we'll be back on time. And you can maybe tackle some of them in Slido while I'm talking. Do you compute an overall KPI from the Taylor diagram, or do you use it for an informed selection of methods?
I'm not sure what KPI is.
Knowledge performance indicator, I believe.
I'll be honest, that's I'm not familiar with what that means to answer on it.
It might also be key performance indicator. So
yeah,
like
that's what I meant.
Some kind of metric, metric for success.
Oh, is it basically kind of like the way that we have like AUC? Can you have like one metric that?
Yeah.
Yes, that's what they're asking.
So, like I said earlier, it's. I don't know. I don't think anybody's come up with any way to summarize the Taylor diagram in one number, and ultimately, harping back to what we were saying earlier, it's best practice not to try and, because even though with like those rock diagrams, we can get like the area under the curve, you're losing a lot of information that could be useful to yourself as the model developer and to your end user. But to answer your question, I don't know personally of a way to kind of get the summary or get the Taylor diagram into like one number.
Okay, thank you. I think there are a few more. If you can go over to the Slido, Monty, and then I'll pop over to my part. But you'll need to actually. You can't do that because you're driving the slides.
I can answer later today, or.
You know what? If you want to swap to me driving the slides, we can.
It's up to you. If you're fine doing that, that's fine.
Let me just make sure I'm on the right slide to drive. Go for it. I'm ready.
Okay, I'm stop sharing, or.
Yes, you stop sharing and I'll share.
Okay.
Okay. That means you can go over to Slido and help answer. That's all. But for anybody else who's helping to monitor Slido, it does now mean that I can't see Slido. So please let me know. Okay. What I'm going to do is, and I'm back to, and I think my camera's back on. I'm sorry. I'm juggling. There it is. Okay. I'm juggling on a laptop. I'm normally on a desktop, but I'm on travel right now. So I'm down to a small screen instead of my usual big one. So I'm Amy McGovern. I'm back. I was trying to give Monty a break in terms of not having him have the whole last hour and a half. What we're going to talk about today is the first part of two parts of talking about XAI methods. So explainable AI methods. Today we're talking about traditional ones, which are ones that traditionally apply traditional machine learning methods, aka not deep learning. But some of the ones we talk about today also apply to deep learning. It's just that the stuff we talk about tomorrow is only deep learning. And then will not necessarily, like saliency maps tomorrow, will not necessarily apply to a random forest, for example, whereas I'm about to talk about permutation importance that could apply to any method. Okay, so before we get going on that, and I can't see the poll, so I'll have to assume Tasia can switch to show the poll. Head over to Slido, and we're going to ask you a quick question to get your thoughts on how you could currently explain traditional machine learning models in a way that will increase trust. And I will stop sharing and assume that Tasia can start sharing the poll so we can see live results. People are thinking hard. I don't see any answers yet. There we go. Okay. Not very well in a way that increases trust for me personally. Average well. Better than some people. Not deviate too much from theory and observation. That's an interesting one. For neural networks, definitely not well enough. I agree. We're going to try to talk about the ways that it exists. Using metrics and plots, integrated gradients, layer-wise relevance propagation. We'll talk about those tomorrow. Depends on the model, but okay. This is, by the way, going to go by so quickly because you guys are doing a great job of answering, and I'm not the one sharing the screen, so I'm missing some things. But there are some good points in here. Avoiding jargon, feature importance. We're about to talk about feature importance. We're going to talk about interpretable versus explainable both today and tomorrow. I like we need to dissuade ourselves from the notion that a single performance metric can perform sufficient to work on trust. I agree with that. using proper metrics, explaining AI as a method of pattern recognition, yes. Still in the hands of the limited people. Well, I hope that we are not, I hope we're trying to get that out there now. Yes, it depends on the field of study. I agree with that. I figured as this started to slow down, we would start to get back to the slides, but yes, we need uncertainty quantification. That's an excellent call out for day 4. Day 4 is going to be all about uncertainty quantification and all the methods for communicating uncertainty, both from the risk communication perspective and the machine learning perspective. Yes, and 100% by using language that the receiver can understand and engage with. Yes, agreed. We can't just dump statistics at people if they're not ready to see it. We need to talk about how to do visualization. That is an excellent one. And that ties in with the one that just came in, having the user perspective in mind. Those are great. I'll give it about 30 more seconds here, and then we will switch back to the slides. SHAP, we're going to talk about SHAP today and SHAP tomorrow. So SHAP for deep learning and SHAP for traditional methods. Okay. I think that is excellent. I will go back and check them out as well, but I'm going to swap myself back over to sharing my slides, assuming that all works here. That's the wrong screen. Wait a minute. I think, sorry, we practiced in advance several things, but we didn't practice getting out of full screen slides, which is what just happened to me. Am I sharing this screen? I don't think I am.
Amy, I might be able to share the slides for you. Which slide? Okay.
I'm good.
All right.
I think I'm good. The problem was I had so many windows open. There we go. We're good. Now we're back to the full screen. Okay. So we're going to go back to, we're going to talk for the next 45-ish minutes about global versus local explainability, and then we're going to talk about very specific methods. There were some that were coming in on that poll, which is why we wanted to stop and look at the poll about specific methods. So for example, we talked about SHAP. SHAP, sorry, will be in what Monty, when we switch back to Monty. I'm going to start with a discussion of global versus local explainability. So global explanations give you some, they are an attempt. And again, if you come back to the answers to the poll that we just did, which were very interesting, many of which said there is no exact right answer right now. I agree with that. There is no exact right answer for explainability right now. And in fact, Monty has a paper under review right now talking about how much the different methods might give you different answers. So there, what a global explanation is it's some attempt to describe that model as a whole. And it is looking at what are the most important features of the model, of the machine learning model, what relationship has been learned using this feature. And then the local explanations are trying to look at individual predictors. So what feature is making the biggest impact on prediction for this example? Or if this value was slightly different, how would you change it? So for example, coming with this slide, you might be looking at the global explanations, you're trying to figure out, I gave it 1,000 features to my random forest, which ones does it actually care about? That's something random forest can do really, really well. The local explanation, we're looking more at, well, if I change the temperature by 2 degrees, what happens to everything? Do I just completely blow my model, or can it handle that? So looking at global explainability, we're going to divide it into 3 categories. We're going to look at feature importance and relevance. So the importance of it is how does this feature contribute to the model's performance? The relevance is how does this feature contribute to the model's prediction? And then we're going to look at feature effects, what the relationship is between this feature's values, or this set of features, this grouping of features, and the model's prediction. And then interactions. It's entirely possible that one feature is interacting with another feature. But I should pause here and say by feature, what we mean is sort of, since we're talking about traditional machine learning right now, what we're traditionally talking about are the attribute value pairs. So we're looking at the attributes, or the features, what we're calling them, so that they are the temperature, or if you're doing statistics, it might be the 90th percentile of the temperature, or the standard deviation of the temperature, anything like that. That's what we mean by features. So how does the 90th percentile of the feature contribute to the model's performance? How does it contribute to its prediction? What happens if, how is it interacting? How does the 90th percentile of temperature, for example, interacting with the 50th percentile of temperature? They should be pretty correlated. So looking at local explainability methods, there are the most common local explanation methods are known as feature attribution. And here, these are really, really simple models. We're making an assumption that our model is literally just a linear model, that we have some features, which here are shown with a phi, and our prediction is literally just a bias function plus some combination of these features. So we have the bias, and then we have the sum of the contribution from each feature. And we can make that assumption. That's what we're going to assume, is that we can go through and we can say that, that we have some explanation for each feature, saying that there's some explanation of the bias, how the average prediction of each one of them, and the sum of the contribution from each feature, and that just explains everything. What we're going to jump into now is we're going to look at what features contribute most to model importance, and specifically we're going to look at feature importance methods. So most machine learning models are pretty greedy in how they learn. So I'm going to stick with random forest as my example. So for example, you could give a random forest 10,000 features. You could give it 1 million features. If most of those are irrelevant, the random forest will figure it out. The key is what the random forest does is it greedily finds the best feature, and then it finds the next best feature and the next best feature. But we need to figure out which ones are actually important, so that if you gave it all of those features, that you can just tell it later on, tell the user, well, you gave me 99% of what you gave me was useless. Let's not use it. But even so, most users aren't going to give it that many features. They're going to give it things they think are important. They really want to know what really turned out to be important. So we can use these feature importance methods to figure out how important each feature is, how much more important they are than the less important features, what the learned relationships among these features might be, and what features are interacting with each other. One of the first methods that came out, this graphic is from a paper that I'm the first author on, so you can find it McGovern et al. And BAMS a couple of years ago, is called Permutation Importance. We didn't introduce the method, I just have the graphic, so if you want to go see the graphic more. It was introduced by Bryman, who introduced random forests. And the idea was that you would take a model, you would train the model, that's what the graphic is showing. So there's the trained model with each one of the features. And then you would permute each one of the features. So you don't change the statistical distribution of the data, but what you do is you break the association between the data and the label. And so then you throw that back into the model and you say, how much did it degrade? So when we shuffle the values, we get a degradation. So by shuffling the values, we maintain the marginal distribution of the features. So we're not introducing any bias. You don't want to just introduce noise because that could do lots of things. But by shuffling it, we simply break any association between that data and the label. Well, if the data was useless, if the random forest didn't use it, then it's not going to change the performance. But if the data was the most important thing the random forest had, then it will change the performance. And so it will change the performance most. So the way that the permutation importance method works is that you permute it one by one, you find the one that's most important, and you say that was most important, and then you can repeat this. So now you can find the second most important and the third most important, etc. So we can do this once with one for loop. There are some limitations to that. We'll talk about that in a second here. Let's start with it. So the limitations are that we don't consider hierarchical structures in the data, so we don't deal with correlations. If feature A and feature B, for example, let's be very specific, temperature 90th percentile versus temperature 75th percentile. Let's say you gave your random forest a whole bunch of statistics about temperature. All of those temperature variables are going to be correlated with each other. We don't necessarily know, and it could be the case even worse. Let's imagine you gave it 90th percentile, 75th percentile, and then for some reason you decided to give it 2 times the temperature. And the statistics about that, those are 100% correlated. The random forest doesn't know anything about the physical data you're giving it, and so the random forest might be picking either one of those at any given time, which can change the importance. So if you have feature A and feature B, and they're both really important, but they're correlated with each other, there's no way for the single pass permutation importance that we just talked about to distinguish that they are really the same feature. And so they might not look as important as they really turned out to be, because it might turn out to be that they're each one getting about half the time. So what we could do is we could, for example, do statistics, do a Coriologram and figure out what's correlated and potentially remove variables that are super highly correlated. So there are some results out there already showing, using the figure on the left here on the slides, that if you have a higher number of correlated variables, then the faster your permutation importance of all your different variables is going to decrease to 0. So you start out with 2 correlated variables. I'm hoping you can see my mouse. That's the solid line. And if you have 5 correlated variables, you're dropping down to 0 much more quickly. So a question might be, how can you estimate feature importance in a way that maintains the feature hierarchies, including these correlations? Lakshmanan et al. Has a method where multiple features are permuted. So the way that this works is that the total importance is not only equal to the sum of the individual importances, but it also includes a term based on the covariance between the features. So the way this works, this is the pseudo algorithm, and then we have a graphic to go with it. The most important feature is permuted. So you did what you just did. You leave that most important feature permuted. And now you re-permute everything to figure out what the second most important feature is. Then you leave that one permuted. You do that again, and you do that again until you do all of the top n. So what we just did a couple of slides ago is traditionally called single pass permutation importance. And this new method is called multi-pass because it is more computationally intensive. It is a multiple pass through the method, through the data. If you have 10,000 features, this is going to be much more computationally intensive, but it is better able to handle correlated features because presumably you'll be able to find the two features that were very close to each other should show up together on the hierarchy. So here's a graphic to go with it, just bringing the graphic that we had from the previous slides and then bringing the graphic where we leave one permuted, and then we go through and check the permutation of all of the others. So as more and more features are permuted, the importance scores that you're getting are relying on higher order covariances, which can often be poorly sampled. And that means that you may not, if you're trying to do a lot of features, the first few may be may be sampled very well, but as you're getting farther and farther down, it may be less and less critically important on your permutation importance. You may be able to say, sometimes people, I guess I would take a small side trip off of that note and say, sometimes people like to read these as sort of the truth. You know, this is the absolute most important thing, and this is the absolute second most important thing. And the key thing to note is that you need to understand what the method is doing, because it's entirely possible that you could do two different methods of sampling, and you might get two different answers of what's the most absolutely important thing. And you also need to do bootstrapping on all of this so that you understand that one permutation importance sampling might in fact only give you one particular answer, and you need to really understand the uncertainty in how important you think that feature actually is. Which gets us to the second bullet point, which is that later iterations of this multiple pass inherit the faults of the previous one. So if you did something wrong on the first pass, the next iteration is kind of stuck because it already has it permuted and it has to deal with the next one. This is part of why you want to do multiple iterations. You want to do bootstrapping on it. But then, of course, you're adding a lot of computational power. This is also a greedy algorithm. It doesn't necessarily consider all permutations of features. If you wanted to do all combinations of features, you're welcome to it, but you better have a lot of computing power. So if you wanted to check, find the n most important or k most important features out of n features, k choose n or n choose k, whichever way I just said, because I'm trying to talk without having a whiteboard in front of me, and professors like to have a whiteboard. That would be that would be a lot of feature combinations to check. This is very computationally demanding, as we're trying to say. Now, one good thing is that it is easily parallelizable. So each one of these passes, if you're trying to just do multiple passes of permutations, are separate from each other and distinct. But it's still, if you want to do this 10,000 times, that means you need 10,000 cores if you're trying to do it in one parallel pass, and that's not something that everybody has access to. One thing to note, up to this point, we've talked about something called the backwards version of permutation importance methods. An alternative is the forward-based method. So one key thing in terms of computational power that we were just talking about is we only had to train the model once, right? We trained the model and then we just permute features. We didn't have to retrain the model with different subsets of features. And that's one of the beauties of what we were just doing. So the backwards method just takes that model and says, I'm going to lop this feature out and then see what happens with a set of features and see what happens to the model. The forward pass says, how well does this feature perform all by itself? So all the other features are removed. How well does this perform? That can be much more computationally intensive, because now you're leaving everything else permuted and just saying, how well is this working? You could, in fact, do sequential forward selection, which is a method of doing feature selection in machine learning, where you train the model one feature at a time. You train it on one feature, then you try to find the second best feature, then the third best feature, but that is very computationally intensive. So getting us back to our thoughts on permutation importance, as I said, multiple permutations are required. And I think that this is something that isn't necessarily as well known in the literature. when you read about people who do permutation importance, I think sometimes they just use scikit-learn and they don't really know what scikit-learn is doing. I will point you to our BAMS paper, which I should have put into the slides as a citation, but that talks about what scikit-learn is actually doing, because it's not actually doing permutation importance, it's doing something called Gini importance. But if you're doing permutation importance, even a single permutation is sometimes insufficient, because you might just get a shuffling that is particularly lucky or particularly unlucky. So you really need to do a whole bunch of permutations and then look at the mean and the standard deviation of your importances. Then we need to think about what we're actually verifying on. Different verification metrics, when we talked about when Monty was talking about the different verification metrics, measure different aspects of model performance. So you need to think about, you're measuring importance, you need to think about what you're measuring importance with relevance to. This gets me back to my people who want to use scikit-learn's importance method without understanding exactly what it's doing. It gives you a very different answer. Gini importance is very different than permutation importance. It doesn't mean that it's wrong, by the way. One of the beauties of the Gini importance is that it's order 1 to compute. It's not computationally inefficient because it's computed while you're growing the tree. It's just that you need to understand the choice between what you're doing, what your model verification statistic is that you really want to know about, and how that means you're getting an importance score and what it means to you. I want to make one last note. There's an alternative to single pass and multi-pass permutation importance called grouped importance, where you take a grouping of permuted or unpermuted features. So I'm going to come back to the temperature example, where we for example, I listed a 90th percentile, 75th percentile, 50th percentile of temperature. If you just want to see how important temperature is, you just permute all of temperature at once. So that's grouped permutation. And that might give you an answer. Again, you need to come back to think about what your task is. If your task is to say, how important was temperature to predicting what I'm trying to predict, then do the grouped, and it's a lot less computationally intensive. Okay, so before we head into SHAP and all of the other methods that Monty's going to do, I'm going to get out of this and have you all share the Slido. Hop over to the Slido and say how you think you could use permutation important methods to improve trust in your AI methods. And I will ask, I think, Tasia to share, because Tasia's the one who can actually show the results live.
While they're filling out the poll too, there's a lot of questions in the Slido.
Oh, I can do that. Now that I'm not sharing, I can do that. Hold on. So the ones, am I not like reloaded? So what I'm seeing is Taylor diagram stuff. Okay, I've tossed 500 predictors at a random forest. I delete the lower half and run random forest again. Repeated until I got 30 predictors, which I arbitrarily liked. What do you think of this? Ooh. I think you're putting in a selection bias into what you're doing. When you said you repeated until you got some that you arbitrarily liked, I'm not a fan of that phrase, because it means that you're choosing somehow to say that you really like a particular set of features, and what makes you say that you like those better than other ones. I would say I would come up with some metric that you're trying to measure and use your metric to decide, even if your goal is to get down to 30 that you really like, come up with a metric that helps you identify what it is that really matters to you. Okay. The loss function in the random forest is Gini impurity, so shouldn't the Gini importance be better? Not necessarily, because the Gini impurity score the point is not that it's better. The point is that they give you different answers. Gini impurity looks at how much data is going down each branch of the tree and how much data is going down to, my Q&A disappeared. How much data goes down to each leaf, and then how many, what your impurity score is at that leaf. And so it is giving you just a different metric than permutation. And my point was not to say that one was better than the other, only that you needed to understand that there was a difference between the two of them. And thank you, Douglas, for putting the paper into the Slido. I'm going to try to watch the poll live now. So permutation importance methods can provide quantitative support for your feature choices. Yes, I agree. That's part of what I was answering with that one question about making sure you have a metric. They can be used to debug the model. Very, very true. You could find out that you have a bug in your data because something turned out to be really, really important, or something you know should have been important and it wasn't, then you could also find out there's a bug. These are going by quickly now. Use permutation importance to see whether the AI method thinks what's important is the same as what I expect a priori based on physics. Agreed. Definitely agreed. That's kind of where we just went with debugging. Increase explainability of the black box. Yes. I think that's really important. It isn't, by the way, in my opinion, I am not saying that this is the answer. This is a piece of the answer. Use a case where the result is already known, then run the permutation model and see if the results are comparable. Yes, it will be sort of where you already know where something's really important and making sure that it shows up as important. That would go back to the debugging or the one that just came in about sanity checks. It can help with selection of variables, which in turn has advantages in simplifying things. I agree with that as well. Definitely, if you're trying to do a model in real time, you're trying to run something in real time, operationally, you want to use a small number of features because you don't, operational meteorologists, unless you're at a company, traditionally don't have lots of supercomputers available to them. NOAA does not have the resources that some of the giant computing companies have. Okay, I think, Monty, I want to give you a chance to tell me, I don't want to cut short your time.
You're talking about getting the next set of slides going?
Yeah, are you good?
Yeah, I think, yeah. And then we can answer other questions.
Oh, and I'm going to answer while you get the slides going. I'm going to answer that top one. How do you apply it if your data are images? That is an excellent question. Go ahead and work on your slides, Monty. I'll answer that one. We're going to talk about that tomorrow, actually. Permutation importance does apply to deep learning. And we will talk about that tomorrow, but the notebooks that are already available, I think when the Trustathon goes live this afternoon, you're going to get a link to a whole bunch of GitHubs and notebooks and things like that. And the notebooks that are available already have some examples of that in there. And now I think it is Monty's turn, and I will turn off my camera. Turn yours back on, Monty.
Oh, okay, there we go. Yeah, a lot of great questions so far. Really digging the everybody kind of participating, asking a lot of really good questions.
Yeah, and I'll hop over into Slido and try to answer things in text now that it's your turn to talk.
Sounds good. One of the things that will immediately come out of, let's say, a permutation importance analysis or any type of feature importance analysis is, why did that feature end up on top? And unfortunately, permutation importance doesn't really tell us that. It can tell us what the top features are, but it doesn't provide an explanation to us as to why are these the top features? What's driving the reason why they hurt the model performance so bad once they're removed? So if we want to better understand our top features, again, going back to what Amy was talking about, so once we know what the top features are, then we know that's where we need to analyze. So once we know what those top features are, we can start doing, looking at exploring how sensitive our model is to a particular feature. So we might want to ask the question, on average, how does the model prediction change when we increase the value or decrease the value? So if we were trying to predict say winter precipitation, how much does whether or not we get snow or rain depend on how the temperature value changes? So that's really kind of what we would start to explore with these next techniques I'm going to talk about. So the most simple way to evaluate our model sensitivity is something that's called partial dependence, which was also one of the very first model explainability techniques ever introduced. And so to compute partial dependence, say for feature X of I, what we'll do is for every single example in our data set, we'll replace feature of X of I's value with a single value. So if we had like temperature, we would replace every single example of temperature with, say, 10 degrees, or as I'll allude to in the graphic on the right, negative 10 degrees Celsius, -2. And we'll do a single value for every single example, and we'll evaluate the model, get the prediction, and then calculate the average. If we repeat that process for multiple values, then we're going to get a curve. And then our last step, once we have that curve, is to subtract out what the average value of that curve is. And this is something I'll describe a little bit down the line. We want to make sure that the mean effect is 0. So basically the curve is balanced around 0 contributions. So in this case, we're looking at partial dependence curves for 3 different machine learning models, trying to predict sub-freezing road conditions in the next hour. So on this example, what we're looking at is 2-meter temperatures. And so we're looking at 2 meters temperatures from -10 degrees Celsius up to 4 degrees Celsius. When we are in the much colder regime, we are seeing that the contribution to the model is positive, and positive 20%, say per se. So, and then for the higher end, so for warmer temperatures, so say once we're above -2 degrees Celsius, the contribution then from this feature is to lower the machine learning probability. So this gives us some idea of, so in this particular case, this was one of the top features for predicting whether or not the road surface temperatures would be sub-freezing. And so in this case, we can kind of get a really good understanding. So we can see that this matches our physical intuition about what should be going on here. And we're getting hopefully this starts to give us a better access to start trusting the model and stuff like that. So we're like, okay, it's matching our physical intuition. This is good. This is a good start. Unfortunately, partial dependence has a couple limitations that can sometimes ruin how useful it can be to us. So just like a lot of other machine learning explainability techniques, it's assuming that the features are independent from each other. And when we do that, we can run into issues. So if we look at this top figure here, our data X1 and X2 are fairly correlated with each other. Now, like I said, what partial dependence is doing is basically saying that I can replace values from anywhere and plug it into the model to see the prediction. We can see that these 2 variables are quite correlated with each other. So if I picked a value down here of, say, 0.75 for X1 and plugged it into the model, well, this part of the data it may not even make physical sense, right? If this was, let's say, updraft speed, so how strong our storm is, and like hail size, you can't possibly have a situation where you have you're predicting 2 or 3 inch hailstones, but your updraft speed is 0. So what that's going to do is that's going to cause the model to make some, it's going to have to extrapolate. And so it may do a very bad job extrapolating, and that may not even be meaningful, what that prediction down there means, since that's not even physically possible. So because of that, that's really going to affect the partial dependence curve that you get. And then the second limitation is that this is only showing you the average effect. So you're not necessarily getting a good idea of how the effect might change once you're in a different part of the phase space and there's other values of other features in that phase space. So in this case, what we're seeing is a flat partial dependence curve, which is what's being shown in yellow. And then what's being shown here in black are called ice curves. So this would be each individual example that goes into making the average for the partial dependence. I won't go into full detail. This does have a hyperlink that you can click on if you want more details. But what this is showing you is that when you look at the effect that this feature has in conjunction with another feature, it actually does have a really strong positive effect, say in this part of the this part of the phase space. But then if the other feature that you're dealing with basically makes it so that the contribution from this feature becomes negative. So when you average them together, it looks like its mean effect is 0, which is very misleading, when in fact we can see it's clearly not having a 0 effect on the model. So the alternative, which has been introduced relatively recently, I think as of 2016, is to compute what's called the accumulated local effects. So rather than looking at the marginal distribution, so I'll hop back here. So, partial dependence is looking at kind of the marginal distribution. ALE is going to be looking at more conditional distribution. So it's going to be looking at making changes to features in small little local areas, as opposed to having this big, huge change. And by doing so, we make ourselves slightly more immune to correlated features. Not fully immune, that can still cause an issue, but we should end up a little bit better off than if we just did the partial dependence route. So what ALE is doing is it's trying to compute the average change in much smaller windows, just these little tiny windows. So in this particular case, let's look at the data and look at like bin number 4. What we'll do is take all the values that are in bin 4. So this is like a particular range. So if X1 was temperature and X2 was like amount of rainfall or something like that as our predictors, then we'd be looking at that particular part of the phase space. And what we're going to do is we're going to take all the examples, put them on the left side of the bin. So rather than like, remember in partial dependence, you can basically replace a value with any other value in the distribution. But for ALE, we're just going to take all the values and put them to the left side of the bin, compute the prediction. Then we're going to replace, for that particular feature, the values with the right side of the bin and compute the average difference. And so that kind of gives us just the average change in just that little part of just kind of a local change. And then we'll do like accumulated sum, basically integrating, and we'll integrate all those little differences, and then that's going to give us the ALE curve. And that makes us a little bit more immune to to the correlated features. So to kind of give you like a comparison of like what I'm talking about like how partial dependence could fail and even ALE could fail. Imagine that we had a data we had data that had this known relationship. It's our target variable equals x1 times x2 times x3. And let's assume that x2 and x3 are pretty strongly correlated with each other. So if we were to fit a machine learning model to this data, we're going to get the PD curves and the ALE curves that you see on the right. So for example, we treat like a random forest. So the top row is the partial dependence curve per feature, and then the bottom row is the ALE curve per feature. And so there's a couple takeaways here. So let's see, I want to move that. One of the takeaways here is that ALE is quite shaky, and that's because we're computing these changes in these little small bins, so that can make the curve a little bit noisy. So that's kind of unfortunate because we were trying to do this local effects, we're not seeing the very clear linear relationship that we would see like in partial dependence. And so you may not walk away with the right conclusion that, okay, X1 is actually linearly related to our target variable. But where partial dependence is failing is that when X3 and X2 are correlated with each other, the real relationship here is actually quadratic. It actually would be y equals x1, x2 squared. And so the ALE is actually giving us a much better indication of the fact that the relationship for x2 and x3 is actually quadratic as opposed to linear. So you can kind of see that there's some plus and minuses there for partial dependence and for the accumulated local effects. So one of the cool things about ALE and partial dependence is that we can actually use them as kind of like an additive description, kind of much like we were talking about with the local feature attributions. So what we've been showing up to this point was kind of like that first order ALE curve. So that's like the first order sensitivity. How much does changing this one feature impact the model prediction? But we can actually scale up ALE and partial dependence to do multiple features. So we can say, okay, how do these 2 features impact the model, or 3 features? Usually can't go beyond 2 because there's no like clean way to visualize it in a way that would be meaningful, for you as the developer, let alone your end user. But it's good to keep this in mind. So if you recall back to when I was describing the partial dependence, and I talked about that we wanted to take out the average so that the mean effect is 0. The reason we do that is because we want to keep in mind that we have this intercept term, which is basically kind of like the average model prediction. And so when you're going to do, say, some of the Trustathon activities, you really want to keep this in mind that you automatically for free have that in your description of the model's prediction. So let's say you had a data set that was balanced. It was like 50% tornadoes, 50% not tornadoes. If you train a machine learning model, then the average model prediction, assuming that your model is reliable, the average model prediction should be 50%. That's what that intercept term is there. And so then any additional effect has to be understood within the context of that, what that base is. So that's, like I said, it's very vital to keep that in mind. Also, when you think about these higher order effects, we won't be talking about it in today's presentation because it's kind of too lengthy to go into. But if you wanted to start understanding second or third or higher order effects, basically understanding how features are interacting with each other, it's this type of framework that you would use to start understanding that and start appreciating that about your machine learning model. So just to kind of, there was problems with partial dependence, but there are problems with ALE as well. As we showed in that example, due to kind of like that local binning, our curve can kind of be shaky, and in which case it may give us a false impression of the learned relationship where, say, for example, that relationship was perfectly linear, but yet the curve kind of made us imply that maybe the relationship wasn't so linear. There's also going to be bias. So obviously, since you're doing the local sampling, you actually need to have enough samples per bin to compute this. And usually most of our distributions are not going to be very well sampled near the end. So we're definitely going to want to put less trust into what the ALE curve is saying towards the end of our distributions. The partial dependence is also much easier to calculate, and it's a little bit easier to understand what's going on, whereas ALE is not as straightforward because you're looking at kind of these local conditional changes as opposed to marginal changes. And so it's going to be much more difficult to code up, and it may be more difficult for you as the developer or your end user to kind of understand what the machine learning model has learned. And then, of course, as you'll find out is the case for basically all explainability methods, it is not completely devoid of the impact of strongly correlated features. If they really are super strongly correlated, then even that local binning is not going to avoid these issues completely. So kind of going to change, so now we've kind of gone in the past two sections with me and Amy, we've been talking about global explainability. So looking at, what are the top features over the whole data set, and what are the learned relationships kind of at these large scales. Now we're going to kind of segue into these feature attribution methods where we're starting to try and understand individual predictions. So if your model says there's a 60% chance of a tornado, can we kind of understand the individual components that are going into that prediction? So when we're using machine learning models and we're interacting with our end users, they're going to kind of want a story behind the prediction, especially if we're talking about decision-making for high-risk situations like severe weather prediction, then your end user is really going to want to be justified in the decisions that they're making. So they're really going to want the story, so to speak, behind the prediction. So let's say we have an example of, like I was alluding to earlier, where your machine learning model is predicting that in the next hour, there's a 60% chance of a tornado passing through city A. Well, why? Why is it saying 60%? And so maybe if we do like a breakdown, we can see that we have like high composite reflectivity. So the storm's really strong. There's like a strong velocity couplet. So there's indications of really strong rotation at lower levels. But we have like a high lifting condensation level. So basically the cloud base is kind of maybe high and not elevated. So this would be very interesting to a forecaster, because the forecaster said, may look at that composite reflectivity and the strong velocity couplet and say, okay, I agree that storm is strong and it is rotating, but the fact that it's elevated and not near the surface, and we really need the cloud to be near the surface for the tornado to form, then perhaps in this case, the forecaster may, bring in their prior beliefs and their prior knowledge and say, I don't really think there's a 60% chance, because the machine learning model in this case is not, perhaps not properly taking into account the fact that the storm's elevated. So how can we try to properly attribute some part of the model prediction to each feature. And this is where Shapley values come in and game theory. So the question at hand is, if you're looking at it from game theory, is how can we, if we have people who pay money into a game of cards or something like that, how can we divide that money up in a fair way between the players? And to put that into the context of machine learning, we're asking, okay, how can we take the model prediction and fairly attribute where that prediction is coming from to each predictor in our model or in our data set? And so by fairness, we're talking about three distinct properties that have to be met. Very first and foremost, we have to satisfy additivity. So the contribution from each feature must equal the final prediction. If we attributed, 80% of the model prediction to like the strong reflectivity and then 30% to say the rotation, well, then we're not even satisfying that basic principle that we're actually equaling, the contributions actually equal the model prediction. We also want to see consistency. So for example, if two features have the same, basically the two features kind of paid the same amount of money, then they should be attributed the same amount. Or if we change our machine learning model in a way that we know is going to make feature A have a stronger effect, then we should see that the contribution from that feature increases likewise. And then lastly, if we were to remove a feature and it's missing now, then its contribution must be zero. It can't be contributing something if it's not playing in the game or being a part of the prediction, so to speak. The cool thing here is that Shapley, the gentleman who came up with this, actually won, I believe, like a Nobel Prize or whatever. Shapley values are the only possible solution that satisfies all three of these properties. So if you've satisfied all three of these properties and you've computed a value, it's the Shapley value. So what is a Shapley value? So if we're talking about a particular feature, say feature X of 1, then the Shapley value is the weighted average difference in the model prediction when X1 is included in a set and not included in a set for all possible feature subsets. So in this case, you can see that we've included the feature X of I, which indicated by the orange dot, and then not included it in some feature subset. That change is indicating what contribution that model or what that feature made to the prediction. And we're going to do that for different subsets. And so the reason why we say weighted is because we could be doing a subset that has almost all the features in it, and we remove one feature. Or we could be doing with a feature subset that has almost no features, and we add X of I in. And so in those cases, we're getting a better indication of what contribution, say, XI is making when we have almost all the features or almost none of the features. And so that we give those a greater weight in the calculation. So that's where the weighted part is coming in. So that's Shapley values. But obviously, for anybody who's kind of thinking about this mathematically, to do all possible feature subsets is pretty difficult. And so it's often kind of impossible to actually compute Shapley values, and I'll kind of get that into the next slide. But in a very cool sense, from developers at Microsoft have come up with this package called SHAP, which stands for Shapley Additive Explanations, which is going to be combining the Shapley values that you saw or that we've been discussing with the concept of feature attribution. So much like that equation that Amy showed earlier, where we're talking about these linear combinations to equal the model prediction, that's what SHAP does. SHAP is going to try and compute Shapley values so that the sum of the Shapley values equals the model prediction. So like I was saying on the previous slide, computing the exact Shapley values is pretty much practically impossible for most realistic data sets, because you have to create a whole lot of feature subsets to kind of compute it that accurately. You also have to deal with the issue of, okay, how do we treat missing features in an ML model, right? Machine learning models are not necessarily designed to have a feature go missing and then make a prediction. Now, I will say that you actually can compute the exact Shapley values within the SHAP package, but this is only if you have like, I think less than 10 features is the only thing that's like even remotely possible within that package. So what we're gonna have to do is try to approximate the Shapley values, and the SHAP package, these two things that I'll talk about are pretty much consistent in the whole package, whether or not you're talking about a deep learning technique, a random forest. Basically what it's going to try and do is only use a small set of feature subsets, but we're going to try and do it in a smart way. So like I was alluding to earlier, the thing that's going to give us the most, that's going to tell us the most about how a feature is contributing is to have almost all the features and then remove the feature of interest, or have almost no features and then put the feature of interest back in. Those are going to tell us the most. So we're going to try and rely on those feature subsets to compute the Shapley values. And then this is where things kind of get kind of interesting to think about. So if we want to replace, if we want to have like missing features in a machine learning model, then usually what's done is to replace the values of that feature with some background or reference data set. So we would take, when a feature or features are missing, we're going to replace their value with some reference value. And then because of the fact that we are using that reference value and it's tied, the Shapley value is now tied to that reference value, to try and get some more robust results, we'll usually repeat the process for say 100 samples. So it'll replace the missing features with 100 different versions of the reference and then compute the sample average to try and give us a little bit more robust measurement of what the Shapley value is. So to kind of jump into how SHAP works, like I was saying, they use this smart feature subsetting. So if you were computing SHAP values or Shapley values from the SHAP package, the default method is called the permutation-based method, in which case, what it's going to do is go with the simplest possible feature subsets, which is basically the forward permutation and backwards permutation, where we will slowly add in features that we're missing and then slowly remove them. And so again, by missing, I'm meaning that you're going to replace it with a reference value. So in this case, X1, X2, and X3, so say that's our data set for our model, all three of them are missing. So they're all going to be, you're going to compute the prediction with all three of them having a reference value. And then what we'll do is we'll add X1 back in. So X1 will remain the value of the example we're trying to explain, and then X2 and X3 are going to be missing. And then when we compute the prediction here and we compute the prediction here and we take the difference, that is the Shapley value for X1. We'll repeat the process where we add X2 in. And so the only difference here is between these two subsets is X2 has been added in. So that's going to give us a Shapley value for X2, then the Shapley value for X3. And then this is where we're going to start doing the backwards permutation. So we have all three features are present, and then we're going to remove or have X1 go missing. So in this case, X1 will be replaced, its value will be replaced with some reference value. And now we'll have the second iteration of the Shapley value for X1, and in which case we would just average these two together, and that'll be the Shapley value for X1. And then we'll have two values for X2 and two values for X3. And at the core of it, this is basically how SHAP is computed. Now, as we've said, kind of leading up to this, that one of the key issues when it comes to model explainability methods is that a lot of them assume that features are independent, which really doesn't work for most of Earth science data because we often have, physical correlations between our features. So the alternative then is to not compute Shapley values, but actually compute the Owen values. This is where we actually respect the feature hierarchies. And this can either be done like manually, you can manually declare what your feature clusterings are going to be, or you can use like feature clusterings based on correlations. And so in this case, rather than say in this previous example, we were removing or adding back in features one at a time. In the Owen value framework, instead of removing or adding back in a single features, we're going to remove multiple features at a time based on the coalitions that we've defined. And so one of the cool parts is that's going to have a better, it's going to better reflect the feature hierarchies. And because we're not having to remove features one at a time, it's also going to make the runtime a lot slower. And so, like I said, when we do Shapley values in this way, they change names and they become known as Owen values. That permutation-based method is the kind of the default model agnostic, so it can be applied to any model approach. But it can be kind of a brute force method. And so there are model specific alternatives that the SHAP package developers have introduced, which are, because they're model specific, they can either be more computationally efficient, which is in the case for neural networks, or offer higher accuracy in the case of tree-based models. So there's, for the neural networks, there's an algorithm that theirs is based off of called deep learning importance features. This uses kind of the back propagation that is built into deep learning models to try and be more computationally efficient rather than doing the different permutations. And then tree-based methods, what's cool is they can actually use the structure of the tree itself to determine what the Shapley values are, which actually returns the exact Shapley value. So it's pretty much the only model that you can probably get, exact Shapley values. Unfortunately, because of having to traverse the tree structure, especially like let's say like a random forest with like 500 trees, it's going to be much longer to run than the permutation-based method. So this is where, you'll have to start doing trade-offs in your mind as the developer of like, okay, I might get slightly more accurate Shapley values, but it's going to take a lot longer to run. So you'll have to, kind of determine maybe I should stick with the permutation-based method or not. So it's definitely, there's a lot of trade-offs when it comes to these explainability techniques, and oftentimes many of them are very computational to run. So sometimes you may have to sacrifice accuracy for runtime. Now, there are a handful of limitations to SHAP. It's a really cool tool, but it does have limitations, much like many of the other model explainability methods. So first of all, it's assuming that a prediction can be represented by a linear combination. This is kind of the fundamental assumption of SHAP. But there has been some research to show that may not be applicable to some models. If you have like certain very complex neural networks or random forests, those models may be very nonlinear in the sense that you would have to think about the combination of the features as being a nonlinear contribution. And so that's definitely a limitation. It's also can be difficult for your end user to try and think about a prediction in that way. We don't really think about model predictions as being this linear combination of different features. And so if you're just talking about the Shapley value for a single feature, it can be very difficult to convey what that means to your end user. As I said, when features are correlated, it can be very difficult to interpret Shapley values. There is the alternative, the Owen values, but then oftentimes you're going to have to declare the feature hierarchies and things like that. So you may run into issues using that. It's a very slow algorithm. SHAP values, even though the developers have implemented some awesome methods to try and increase the speed, you do have it can be very, very slow to run, say, for multiple number of examples. And if you have a large number of features, CHAP can be very slow to compute compared to other feature attribution methods, which we did not discuss today. There's also no indication of strong feature, or you don't really get to understand feature interactions when you're looking at Shapley values. So for example, if you're using this, you might get a certain, let's say you're trying to understand a particular example and you see the Shapley breakdown. And then you go look at like another example that's very similar, but maybe the temperature values ever so slightly different. And the Shapley value breakdown could look totally different. It can be very difficult to understand why, despite having very similar features, the Shapley breakdown is so different. And that's because of the fact of strong or feature interactions can really change Shapley values quite a bit.
Hey, Monty, we need to cut to the end real quick. I know you're on your last slide, but we have to do a couple of things to wrap up.
I thought I was going really fast last time, so I slowed down. Okay.
You did an excellent job. I need 30 seconds.
Okay, so the last thing is that you're always going to have a reference data set to do those missing features, which could be difficult in operational settings. They can't always be chugging around like, megabytes worth of data. I'm not sure, but so yeah. So that's it from my end.
Okay, we have a couple of quick, can you stop sharing? Because I had to do one update to the slides and it won't reload. Okay, thank you. So DJ is going to come on and make a quick announcement about the, especially because my sharing is not showing. DJ is going to come on and make a quick announcement about the Trustathon. You do that, DJ, while I get the slides up.
Okay, so quick announcement. I'll be doing a kickoff video at 1 p.m. To introduce the Trustathon and kind of go through the instructions of how to get started. In the meantime, I have posted a getting started blog post if you want to start reading through the instructions, and I'll share that on the Slack.
Thank you. And then the last thing I was going to say, we will try to take a quick pass through all the Slido questions that are left, but I realized as I was going through the questions that I left a sponsor off this morning, and so I have retroactively fixed the slides, and I don't want to end without saying that we missed the NOAA Center for Artificial Intelligence on our list of sponsor slides. What's going to happen is those of you who are in the Trustathon should already be in the Slack. You should have gotten in the last half hour invitations for the blog posts as well. And if you have questions, get onto the Slack, start asking them, and we're going to get this going. It's going to be really fun, and then we'll be back tomorrow for the lectures. Thank you. And and is there, DJ, are you coming back live here, or you're just doing a non-live?
I think we're discussing that. I think I will post a video on Slack instead of coming back here, so that we can. It'll be available to anyone who is coming in at a later time.
Okay, so DJ's good. You don't need to come back to the live stream. DJ's going to post everything on Slack for everybody who's doing Trustathon. See you all tomorrow. Thank